sklearn datasets. Description: explain in detail. The scikit-learn sklearn library in Python provides a collection of datasets commonly used for machine learning tasks. These datasets are readily available and can be used to experiment with various algorithms, understand their performance, and develop machine learning models. Inputs. Input 1. Explain in detail. None. The datasets are pre-built and directly loaded from the sklearn library. Input 2. Explain in detail. None. Outputs. Output 1. Explain in detail. The datasets are returned as NumPy arrays or pandas data frames, depending on the specific dataset. These arrays data frames contain the features and target values for the machine learning task. Output 2. Explain in detail. In some cases, the datasets may also include additional information, such as descriptions of the features, target variables, and other relevant details. Steps. Step 1. Explain in detail. The datasets are loaded using the appropriate function from the sklearn datasets module. For example, from sklearn datasets import load iris. From sklearn datasets import load digits. And from sklearn datasets import load breast cancer. Step 2. Explain in detail. Once loaded, the datasets can be accessed as attributes of the returned object. For example, to access the features of the iris dataset, you would use iris data. To access the target values, you would use iris target. Metrics. Metric 1. Explain in detail. The datasets are not inherently associated with metrics. Metrics are evaluated on the models trained using these datasets. Common metrics include accuracy, precision, recall, F1 score, and mean squared error, depending on the task. Metric 2. Explain in detail. The datasets may contain pre-computed metrics, such as the mean and standard deviation of features. But these are not the primary metrics used for evaluating models. Visualization plots. Visualization plot 1. Explain in detail. Visualization plots are typically created using the data from the datasets. For example, you might create scatter plots, histograms, or box plots to visualize the relationships between features and the target variable. Visualization plot 2. Explain in detail. Libraries like Matplotlib and Seaborn can be used to create these visualizations. Fine-tune parameters. Parameter 1. Explain in detail. The datasets themselves generally don't have tunable parameters. The parameters that need tuning are associated with the machine learning models trained on these datasets. Parameter 2. Explain in detail. For example, in a support vector machine SVM model, parameters like C regularization parameter and gamma kernel coefficient can be tuned to improve model performance. Uncertainty methods. Uncertainty method 1. Explain in detail. The sklearn datasets themselves do not include uncertainty estimates. Uncertainty methods are typically applied to machine learning models trained on these datasets. Uncertainty method 2. Explain in detail. For example, Bayesian methods can provide uncertainty estimates for model predictions. Challenges and fixes. Challenge 1. Explain in detail. Dataset imbalance. In some datasets, one class may be significantly overrepresented compared to others. This can lead to biased models that favor the majority class. Sample use case that resulted in challenge 1. A dataset where 90 of samples belong to class A and 10 belong to class B. A model trained on this dataset might perform well on class A but poorly on class B. Fixes to challenge 1. Techniques like oversampling, replicating minority class samples, undersampling, removing majority class samples, or using cost-sensitive learning algorithms can help address class imbalance. Challenge 2. Explain in detail missing values. Datasets might contain missing values in some features. Sample use case that resulted in challenge to a dataset with features like age, income, and education. Some samples might have missing values for specific features. Fixes to challenge 2. You can address missing values by either discarding the corresponding samples, imputing missing values using various techniques, e.g., mean imputation, KNN imputation, or using algorithms that are robust to missing values. sklearn, datasets, clear data home. Description: explain in detail. Input 1. Explain in detail. This method takes no input parameters. NA. This method does not return any output. NA. Step 1. Explain in detail. The clear data home method removes all downloaded datasets from the data directory specified in the data home parameter. This method is used to free up storage space if you no longer need the downloaded datasets. Metric 1. Explain in detail now. NA. Visualization plot 1. Explain in detail now. NA. 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 Accidentally clearing data directory could lead to losing important datasets. Running the clear data home method without confirming the desired action. Double-check the directory path and make sure you want to clear the data before executing pay function. NA. 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 sklearn, datasets, dumps VM lite file. Description: the dumps VM lite file function is used to save sparse data in the LIBS VM format. It's commonly used for training and testing machine learning models, especially linear models. Inputs: X. This is a NumPy array or a sparse matrix representing the feature matrix independent variables of the dataset. Each row corresponds to a data point, and each column represents a feature. Y. This is a NumPy array representing the target values dependent variables of the dataset. It has the same number of elements as the number of rows in X, with each element corresponding to the target value for the corresponding data point. F. This is the file path where the data will be saved in LIBS VM format. 0 based. This parameter indicates whether the feature indices should be 0 based starting from 0 or 1 based starting from 1. The default value is true for 0 based indexing. Comment. This optional parameter allows you to add a comment line at the beginning of the file. This comment is typically used to provide information about the dataset. dtype. This parameter specifies the data type of the feature values and target values. The default value is float 64. Outputs. Output file. The function writes the data to the specified file path F in LIBS VM format. This format is widely supported by various machine learning libraries and tools. Steps. Data conversion. The function converts the input data X and Y to the LIBS VM format, which is a text-based format suitable for sparse data representation. File writing. The converted data is then written to the specified file F. Challenges and fixes. Challenge 1. Data type mismatch. If the data types of X and Y are not compatible with the specified dtype, the function may raise an error. Sample use case that resulted in challenge 1. Attempting to save data with integer features in a target variable of type string. Fixes to challenge 1. Ensure that the data types of X and Y match the specified dtype before calling the function. Convert any incompatible data types to the appropriate format. Challenge 2. Incorrect feature indexing. If 0 based is not set correctly, the feature indices in the output file may be incorrect, leading to errors in training or loading the data. Sample use case that resulted in challenge 2. Saving data with 0 based set to false, but the features are expected to be 0 based. Fixes to challenge 2. Set the zero-based parameter correctly to match the actual indexing of pay features in the data. If the features are zero-based, use zero-based true. If they are one-based, use zero-based false. sklearn, datasets, fetch 20 newsgroups. Description. This function fetches the 20 newsgroups dataset, a collection of approximately 20,000 newsgroup documents partitioned across 20 different newsgroups. It is a widely used dataset for text classification and natural language processing tasks. Inputs. Data home, the directory where the dataset is stored. If none, it will be stored in the scikit-learn data directory. Subset selects a subset of the dataset. The options are train, test, all. Categories, a list of newsgroups to include in the dataset. If none, all newsgroups are included. Shuffle, whether to shuffle the dataset. Random state controls the shuffling process if shuffle is true. Remove a list of strings to remove from the dataset. Download if missing if false. Raise a I/O error if the data is not locally available instead of trying to download the data from the source site. Create directory if true. Create the directory data home if it doesn't exist. Transform, whether to use a simple preprocessing transform that removes punctuation, converts to lowercase, and applies stop word removal. Outputs. Dataset, a dictionary-like object containing the following keys. Data, an array of strings containing the text documents. Target, an array of integers representing the target labels for each document. Target names, a list of the names of the target categories. DESCR, a string describing the dataset. File names, an array of strings containing the file names of the documents. Steps. Downloads the 20 newsgroups dataset from the source site if it is not available locally. Extracts the relevant data based on the input parameters. Preprocesses the data if the transform parameter is set to true. Metrics. Accuracy, a measure of the percentage of correctly classified documents. Precision, a measure of the percentage of correctly predicted positive cases out of all positive predictions. Recall, a measure of the percentage of correctly predicted positive cases out of all actual positive cases. F1 score, a harmonic mean of precision and recall. Visualization plots. Confusion matrix, a visual representation of the classification performance, showing the number of correctly and incorrectly classified documents for each class. Word cloud, a visual representation of the most frequently occurring words in the dataset. Fine-tune parameters. Categories, the choice of categories significantly affects the model performance. Selecting categories with distinct topics can lead to better accuracy. Transform, using preprocessing techniques such as stop word removal and stemming can improve model performance by removing irrelevant words and reducing the dimensionality of the data. Uncertainty methods. Bayesian methods. These methods can estimate the uncertainty in model predictions by considering the distribution of possible model parameters. Ensemble methods. These methods combine multiple models to improve prediction accuracy and provide an indication of uncertainty by measuring the disagreement among models. Challenges and fixes. Challenge 1. The dataset contains a large amount of noise, including irrelevant words, misspellings, and slang. Sample use case that resulted in challenge 1. A model trained on the raw dataset might learn to associate certain irrelevant words with specific categories, leading to poor performance on unseen data. Fixes to challenge 1. Preprocessing techniques such as stop word removal, stemming, and lemmatization can reduce noise and improve model performance. Using a robust classification algorithm that is less sensitive to noise. such as support vector machines or naive Bayes. Challenge 2: the dataset is imbalanced, with some categories having significantly more documents than others. Sample use case that resulted in challenge 2: a model trained on the imbalanced dataset might be biased towards the majority classes, leading to poor performance on minority classes. Fixes to challenge 2: using data augmentation techniques to increase the number of documents in minority classes. Using a classification algorithm that is designed to handle imbalanced datasets, such as random forest or XGBoost. Adjusting the class weights in the classification algorithm to give more weight to minority classes. sklearn datasets, fetch 20 newsgroups vectorized. Description: this function fetches the 20 newsgroups dataset, which is a collection of approximately 20,000 newsgroup documents, partitioned across 20 different newsgroups. The dataset is pre-processed and vectorized, with each document represented as a sparse vector of TF-IDF values. Inputs: subset a string specifying the subset of the dataset to load. Options include train, test, all, or none. Default: train loads the training set, test loads the test set, all loads both, and none loads the entire dataset. Remove a list of strings indicating categories to remove from the dataset. By default, these categories are excluded: comp, graphics, sci.med, talk, religion, miscellaneous. Data home: a string specifying the location to store the dataset. If not specified, it will be stored in scikit-learn data. Download: if missing, a boolean specifying whether to download the dataset if it is not found locally. By default, it is set to true. Return C: a boolean indicating whether to return the data and target arrays separately. By default, it is set to false. Shuffle: a boolean indicating whether to shuffle the data. By default, it is set to true. Outputs: dataset and object containing the dataset. The dataset object contains several attributes, including data, a sparse matrix of TF-IDF values representing the documents. Target, an array of integers representing the target labels for each document. Target names, a list of strings representing the names of the newsgroups. DESCR, a string describing the dataset. X, a sparse matrix of TF-IDF values representing the documents only returned if return C is set to true. Y, an array of integers representing the target labels for each document only returned if return C is set to true. Steps: downloads the dataset from the internet if it is not already present locally. Loads the pre-processed and vectorized dataset from the downloaded archive. Selects the specified subset of the data. Train, test, all, or none. Removes the specified categories from the dataset. Shuffles the data if shuffle is set to true. Returns the dataset object or the data and target arrays separately depending on the return C. Parameter: metrics. Accuracy measures the percentage of correctly classified documents. Precision measures the proportion of correctly classified positive samples among all samples classified as positive. Recall measures the proportion of correctly classified positive samples among all actual positive samples. F1 score, a harmonic mean of precision and recall. Visualization plots. Scatter plot: visualize the data points in a 2D or 3D space using dimensionality reduction. Techniques like PCA or tsna. Word cloud: represent the most frequent words in the dataset. Heatmap: visualize the correlations between different categories. Fine-tune parameters. Subset: adjust the subset of the dataset to use depending on the specific task. Remove categories that are not relevant to the task at hand. Uncertainty methods. Bayesian inference estimate the uncertainty in the model's predictions. Monte Carlo dropout introduce randomness in the model's weights to estimate uncertainty. Challenges and fixes. Challenge 1 class imbalance. Some newsgroups are more heavily represented than others. Sample use case that resulted in challenge 1. A model trained on an imbalanced dataset might perform poorly on underrepresented categories. Fixes to challenge 1. Oversampling duplicate samples from underrepresented categories. Undersampling remove samples from overrepresented categories. Weighted loss functions assign higher weights to underrepresented categories during training. Challenge 2. High dimensionality. The TF-IDF vectors have a large number of features, which can lead to computational inefficiency and overfitting. Sample use case that resulted in challenge 2. A model trained on high-dimensional data might overfit to the training set and generalize poorly to unseen data. Fixes to challenge 2. Feature selection. Select the most informative features to reduce dimensionality. Dimensionality reduction. Apply techniques like PCA or T-SNE to reduce dimensionality. Regularization. Add a penalty to the model's loss function to prevent overfitting. sklearn. Datasets. Fetch California Housing. Description. The Fetch California Housing function from scikit-learn provides a convenient way to access the California Housing dataset, a popular benchmark dataset in machine learning for regression tasks. This dataset contains information on various aspects of residential housing in California, including location, population, median income, and house value. Inputs. Data source. The function retrieves the dataset from a remote source, typically a public repository. This ensures that you are working with a standardized version of the dataset. Data format. The data is typically downloaded in a standardized format, such as CSV or a similar format readily compatible with scikit-learn. Outputs. Dataset object. The Fetch California Housing function returns a scikit-learn bunch object. This object is a dictionary-like structure containing the following key-value pairs. Data. A NumPy array containing the features input variables of the dataset. Each row represents a housing instance, and each column represents a feature. Target. A NumPy array containing the target variable output variable, the median house value. Feature names. A list of strings specifying the names of the features in the dataset. This is helpful for understanding the data and for interpreting results. DESCR. A string containing a detailed description of the dataset, including information about the source, the features, and the target variable. Remote data. The function often downloads the data from a remote source and stores it locally in a temporary directory. This allows you to access the dataset without needing to manually download it. Steps. Fetch data. The function first attempts to locate a cached version of the dataset on your local machine. If the dataset isn't found locally, it retrieves it from the remote source. Load and preprocess. The retrieved data is then loaded and preprocessed into a format suitable for use with scikit-learn's machine learning algorithms. This might include tasks like handling missing values, transforming features, e.g., scaling or one-hot encoding, splitting the data into features and target variables. Metrics. Mean absolute error. The average absolute difference between the predicted and actual house values. Root mean squared error. RMSE. The square root of the average squared difference between the predicted and actual house values. R squared. A measure of how well the model explains the variance in the data. ranging from 0 no explanation to 1 perfect explanation. Visualization plots. Scatter plots visualize the relationship between different features and the target variable house value. This can reveal potential patterns or correlations in the data. Histograms show the distribution of individual features, which can help in understanding their characteristics and identifying outliers. Fine-tune parameters. Model selection. Explore different machine learning models, e.g., linear regression, decision trees, random forests to find the best fit for the data. Hyperparameter tuning. Adjust the parameters of the chosen model, e.g., regularization strength, number of trees in a random forest to optimize performance. Uncertainty methods. Confidence intervals. Use methods like bootstrapping or Bayesian inference to estimate uncertainty in the model's predictions. Ensemble methods combine multiple models, e.g., bagging, random forests to reduce variance and improve robustness. Challenges and fixes. Challenge 1. Data imbalance. Sample use case. The dataset might have an imbalanced distribution of house values, leading to biased models. Fixes. Oversampling. Duplicate instances of underrepresented house value categories. Undersampling. Remove instances from overrepresented categories. Weighted loss functions. Assign higher weights to underrepresented categories during training. Challenge 2. Missing values. Sample use case. The dataset might contain missing values for certain features. Fixes. Imputation. Fill in missing values using techniques like mean imputation or k-nearest neighbors. Feature engineering. Create new features that handle the missing data, e.g., indicator variables for missing values. Challenge 3. Feature scaling. Sample use case. Features on different scales can impact model performance. Fixes. Standardization. Center and scale features to have a mean of 0 and a standard deviation of 1. Normalization. Rescale features to a specific range, e.g., 0 to 1. Challenge 4. High dimensionality. Sample use case. The dataset might have a large number of features, which can lead to overfitting and computational challenges. Fixes. Dimensionality reduction. Apply techniques like principal component analysis (PCA) or feature selection to reduce the number of features. Challenge 5. Outliers. Sample use case. Outliers in the data can disproportionately influence the model's learning process. Fixes. Robust regression. Use models that are less sensitive to outliers. Data cleaning. Identify and remove outliers if they are deemed to be erroneous. sklearn. Datasets. Fetchcov type. Description. None. Dataset. A dictionary-like object with the following keys. DESCR. A string describing the dataset. Data. A NumPy array of shape 581012. 54 containing the features. Target. A NumPy array of shape 581012. Containing the labels. Feature names. A list of strings containing the names of the features. Target names. A list of strings containing the names of the target classes. Loader. A callable object that can be used to reload the dataset. The dataset is downloaded from the UCI machine learning repository. The dataset is loaded into memory and processed. The dataset is returned as a dictionary-like object. Accuracy. Precision. Recall. F1 score. Scatter plot of the features. Confusion matrix. ROC curve. None. None. Challenge 1. The dataset is very large and can take a long time to load. Sample use case that resulted in challenge 1. Training a model on the entire dataset can be slow. Fixes to challenge 1. Use a smaller subset of the dataset for training. Challenge 2. The dataset is unbalanced. with some classes having many more samples than others. Sample use case that resulted in challenge 2. A model trained on the unbalanced dataset may be biased towards the majority classes. Fixes to challenge 2 use techniques such as oversampling or undersampling to balance the dataset. sklearn datasets, fetch KDD Cup 99. Description. Inputs. None. Dataset: a dictionary-like object containing the KDD Cup 1999 dataset. It includes the following keys. Data: a NumPy array of shape 494021. 41 containing the features of each instance. Target: a NumPy array of shape 494021. Containing the labels of each instance. DESCR: a string describing the KDD Cup 1999 dataset. Feature names: a list of strings containing the names of the features. Target names: a list of strings containing the names of the target classes. Loader: a callable object that can be used to load the dataset again. Steps. Download the KDD Cup 1999 dataset from the UCI Machine Learning repository. Load the data into a NumPy array. Extract the features and labels from the data. Metrics. Accuracy: the percentage of correctly classified instances. Precision: the proportion of correctly predicted positive instances among all predicted positive instances. Recall: the proportion of correctly predicted positive instances among all actual positive instances. F1 score: the harmonic mean of precision and recall. Visualization plots. Scatter plot of the features. Histograms of the features. Confusion matrix. None. None. Challenge 1: the dataset is very large and can be slow to load. Sample use case that resulted in challenge 1: training a machine learning model on the entire dataset can take a long time. Fixes to challenge 1. Use a smaller subset of the data for training. Use a faster machine learning algorithm. Challenge 2: the dataset is highly imbalanced, with many more normal instances than attack instances. Sample use case that resulted in challenge 2: a machine learning model trained on the entire dataset may be biased towards predicting normal instances, even if the actual instance is an attack instance. Fixes to challenge 2. Use oversampling or undersampling to balance the dataset. Use a machine learning algorithm that is less sensitive to class imbalance. Challenge 3: the dataset contains many categorical features, which need to be encoded before they can be used by machine learning algorithms. Sample use case that resulted in challenge 3: trying to train a machine learning model on the raw data may result in an error, as the model cannot handle categorical features. Fixes to challenge 3. Use one-hot encoding to encode the categorical features. Use a machine learning algorithm that can handle categorical features directly. Challenge 4: the dataset contains many missing values. Sample use case that resulted in challenge 4: trying to train a machine learning model on the raw data may result in an error, as the model cannot handle missing values. Fixes to challenge 4. Impute the missing values. Use a machine learning algorithm that can handle missing values. YAML. sklearn datasets, fetch LFW pairs. Description. Inputs. Data: home, the directory where the LFW dataset is stored. If not specified, it is saved to the default data directory. Subset controls which subset of the data is used. Possible values are train, test, and 10 folds. Color determines whether the data will be loaded as grayscale gray or color. Resize if set to true. The images are resized to 60 by 60 pixels. Funneled determines whether to use the funneled version of the LFW dataset, which contains only the most common people. Download if missing if true. Download the dataset from the internet if it's not found in the specified data directory. Data A 2D NumPy array containing the images. Each row is a flattened image. Target A 2D NumPy array indicating whether the pairs of images are similar 1 or different 0. Pairs a list of pairs of images, where each pair is a tuple containing the indices of the two images in the data array. Target names a list of names corresponding to the people in the images. DESCR a string describing the LFW dataset. Steps. The data is loaded from the specified directory, or downloaded if it is not found. The images are pre-processed, including resizing and conversion to grayscale or color. The pairs of images are constructed based on the specified subset and funneling parameters. The target labels are assigned to each pair of images, indicating whether they are similar or different. Metrics. Accuracy, the proportion of correctly classified pairs similar or different. Precision, the proportion of correctly classified pairs among those predicted as similar. Recall, the proportion of correctly classified similar pairs among all actual similar pairs. F1 score, the harmonic mean of precision and recall. Visualization plots. Scatter plot showing the distribution of similar and different pairs in feature space. Confusion matrix visualizing the performance of a classifier trained on the data. Image grid displaying example pairs of images, labeled as similar or different. Subset experimenting with different subsets of the data can influence the performance in generalization of the model. Resize, the image size can affect the computational cost and the performance of the model. Funneled, using the funneled version of the dataset can improve model performance by reducing the number of people to learn from, but may limit the generalization to less common faces. Bayesian model averaging ensemble methods can be used to estimate the uncertainty of the models. Predictions. Confidence intervals estimate the variability of the model's predictions based on the training data. Dropout, introducing noise during training can be used to estimate the uncertainty of the models. Predictions. Challenge 1, data imbalance, the dataset may contain a higher proportion of different pairs compared to similar pairs. This can lead to biased model performance favoring the prediction of different pairs. Sample use case that resulted in challenge 1, training a classifier on the LFW dataset with default settings may result in a higher accuracy but lower precision and recall for similar pairs. Fixes to challenge 1. Oversampling, increase the number of similar pairs in the training set by duplicating or generating synthetic samples. Undersampling, reduce the number of different pairs in the training set. Weighted loss function, assign higher weights to similar pairs in the loss function to emphasize their importance during training. Challenge 2, high dimensionality, the images have a high number of features pixels, leading to computational challenges and potential overfitting. Sample use case that resulted in challenge 2, training a complex model on the full resolution. Images may lead to overfitting and poor generalization on unseen data. Fixes to challenge 2. Dimensionality reduction, apply techniques like principal component analysis (PCA) to reduce the number of features. Feature selection, identify and select the most informative features for the task. Regularization, introduce penalties in the model's loss function to prevent overfitting. sklearn, datasets, fetch LFW people. Description. The fetch LFW people function from scikit-learn is used to load a dataset containing images of faces of different individuals. This dataset is useful for tasks such as face recognition, face clustering, and other image classification problems. Inputs. Data home optional path to the location where the data should be downloaded and stored. If not provided, the data will be downloaded to the default data directory, usually scikit learn data. Funneled optional. Default true if true. Uses a funneled version of the dataset, which contains a subset of images where the faces are more centered and aligned. Resize optional. Default 0.5 the size of the images to be resized. The images are resized to resize. Resize. Download if missing optional. Default true if true. Download the data from the internet if it is not present on the local machine. Color optional. Default false if true. Download and use the color version of the dataset. Slice optional. Default none and optional tuple start. Stop. Step that can be used to select a subset of the images. Select channels optional. Default none if not none. Only the specified channels are loaded from the dataset. Outputs. Data a NumPy array of shape n samples. N features containing the pixel data of the images. Each image is represented as a flattened vector. Target a NumPy array of shape n samples, containing the labels of the images. The labels correspond to the person's name in the dataset. Target names a list of strings containing the names of the individuals in the dataset. DESCR a string containing a description of the dataset. Images a NumPy array of shape n samples. H. W containing the images, where H and W are the height and width of the images. Image paths a list of strings containing the paths to the images in the dataset. Steps. Download the dataset if the dataset is not present on the local machine. It will be downloaded from the internet. Load the images. The images are loaded from the downloaded files. Preprocess the images if funneled is true. The images are preprocessed to be more centered and aligned. If resize is specified, the images are resized to the desired size. Create the feature vectors. Each image is flattened into a single vector. Create the labels. Each image is labeled with the name of the individual in the image. Metrics. Accuracy the percentage of correctly classified images on a test set. Precision the proportion of correctly classified images among all images predicted as belonging to a certain class. Recall the proportion of correctly classified images among all images that actually belong to a certain class. F1 score the harmonic mean of precision and recall. Visualization plots. Histogram of the number of images per person. This plot shows the distribution of the number of images for each person in the dataset. Scatter plot of the first two principal components. This plot can be used to visualize the relationships between different individuals in the dataset. Fine-tune parameters. Funneled adjust whether to use the funneled version of the dataset. Using funneled data can improve performance but may also lead to reduced variability. Resize control the size of the images. Smaller images will have fewer features and may result in faster training but could impact performance. Color determine whether to use the color or grayscale version of the dataset. Color information can be helpful for some tasks, but grayscale images may be more computationally efficient. Uncertainty methods. Confidence scores. The model can provide confidence scores for each prediction, which can be used to measure uncertainty. Bayesian methods. Bayesian approaches can be used to incorporate prior knowledge and estimate the uncertainty of the model's predictions. Challenges and fixes. Challenge 1 class imbalance. The dataset is inherently imbalanced. with some individuals having many more images than others. Sample use case that resulted in challenge 1 training a model on this dataset without addressing the class imbalance may lead to poor performance for individuals with fewer images. Fixes to challenge 1. Oversampling increase the number of images for underrepresented classes by duplicating existing images. Undersampling reduce the number of images for overrepresented classes. Weighted loss function assign higher weights to samples from underrepresented classes during training. Challenge 2 image quality. The quality of the images in the dataset can vary significantly. Sample use case that resulted in challenge 2 low quality images can make it difficult for the model to learn accurate features. Fixes to challenge 2. Data augmentation. Generate new images from existing images by applying transformations such as rotation, cropping, and flipping. Preprocessing. Apply image enhancement techniques such as contrast adjustment and noise reduction. Use a robust model. Choose a model that is less sensitive to variations in image quality. Challenge 3 small dataset size. The dataset may be too small to train a complex model effectively. Sample use case that resulted in challenge 3 a model trained on a small dataset may overfit to the training data and perform poorly on unseen data. Fixes to challenge 3. Data augmentation. Generate new images from existing images to increase the size of the dataset. Transfer learning. Use a pre-trained model trained on a larger dataset and fine-tune it on the LFW dataset. Use a simpler model. Choose a model with fewer parameters to reduce the risk of overfitting. Challenge 4 occlusion and variations. Impose. The images in the dataset may contain occlusions and variations in pose. Sample use case that resulted in challenge 4 occlusion and variations in pose can make it difficult for the model to learn accurate features. Fixes to challenge 4. Data augmentation. Generate new images with occlusions and variations in pose to make the model more robust. Use a robust model. Choose a model that is less sensitive to variations in pose and occlusion. Train with more data. Train the model with a larger dataset that contains a wider range of poses and occlusions. Challenge 5 facial expression. The images in the dataset may contain different facial expressions. Sample use case that resulted in challenge 5 facial expressions can affect the appearance of the face, making it difficult for the model to generalize. Fixes to challenge 5. Data augmentation. Generate new images with different facial expressions to make the model more robust. Use a robust model. Choose a model that is less sensitive to variations in facial expressions. Train with more data. Train the model with a larger dataset that contains a wider range of facial expressions. sklearn, datasets, Fetch-Olivetti faces. Description. The Fetch-Olivetti faces function in scikit-learn provides a convenient way to load the Olivetti faces dataset. A collection of face images suitable for tasks such as face recognition and classification. Inputs. Data home path to the directory where the Olivetti faces dataset will be downloaded and stored. Download if missing indicates whether to download the dataset if it's not found in the data home directory. Defaults to true, which means the dataset will be downloaded automatically if it's not present. Shuffle flag indicating whether to shuffle the data. This can be helpful for randomizing the order of samples during training and testing. Random state seed for the random number generator used for shuffling the data. Return seed determines whether to return the data and labels separately or as a single dictionary. If set to true, it returns two arrays, an array of images X and an array of corresponding labels Y. If false, the default, it returns a dictionary with keys data, target, DESCR, and images. Outputs, data array of shape 400, 4096 containing the flattened images. Each row represents a single image with 4096 pixels 64 by 64. Target array of shape 400, containing the labels for each image, corresponding to the identity of the person depicted. Values range from 0 to 39. DESCR string containing a description of the dataset. Images array of shape 400. 64. 64 containing the raw images. Each row represents an image with 64 rows and 64 columns. Steps. Download the dataset if it's not already present in the data home directory. Load the data from the downloaded file or the local directory. Optionally shuffle the data based on the shuffle flag. Return the data and labels either separately or as a dictionary based on the returnC parameter. Metrics. Accuracy commonly used to evaluate the performance of face recognition models. Measuring the percentage of correctly classified faces. Precision measures the proportion of correctly predicted positive faces out of all positive cases predicted by the model. Recall measures the proportion of correctly predicted positive faces out of all actual positive cases. F1 score a harmonic mean of precision and recall, providing a balanced evaluation of the model's performance. Visualization plots. Image display plotting individual face images from the dataset to visualize their appearance and characteristics. PCA visualization applying principal component analysis PCA to reduce the dimensionality of data and visualize the relationships between different faces in a lower dimensional space. Confusion matrix generating a confusion matrix to analyze the classification performance of a face recognition model and identify areas where the model might be making errors. Fine-tune parameters. Data home you can customize the location where the dataset is stored. Shuffle you can disable shuffling if you want to process the data in the original order. Random state set a specific seed for reproducibility. Uncertainty methods. Bayesian methods incorporating prior knowledge about face recognition to estimate uncertainties and improve predictions. Ensemble methods training multiple face recognition models and combining their predictions to reduce variance and improve robustness. Dropout randomly dropping out neurons during training to prevent overfitting and encourage the model to learn more robust features. Challenges and fixes. Challenge 1 data imbalance. Some individuals might have more images than others in the dataset, potentially leading to biased models that favor those individuals. Sample use case that resulted in challenge 1 a face recognition model trained on an imbalanced dataset might struggle to correctly recognize individuals with fewer training images. Fixes to challenge 1. Oversampling duplicating images of underrepresented individuals to increase their representation in the training dataset. Undersampling removing images of overrepresented individuals to balance the dataset. Weighted loss functions assigning higher weights to losses associated with underrepresented individuals during training. Challenge 2 data variability. Facial variations such as pose, lighting, and expression can significantly affect face recognition performance. Sample use case that resulted in challenge 2 a model trained on frontal face images might fail to Recognize faces captured at different angles or under varying lighting conditions. Fixes to challenge 2. Data augmentation, generating artificial variations of existing images, e.g., by rotating, scaling, or adding noise to increase the diversity of training data. Feature extraction, employing robust feature extraction methods that are less sensitive to variations in pose, lighting, or expression. Transfer learning, using pre-trained models on large datasets of faces to initialize a model and enhance its ability to generalize to different variations. YAML. sklearn datasets FetchOpenML. Description. The FetchOpenML function in scikit-learn sklearn provides a convenient way to access and load datasets from the OpenML repository. OpenML is a platform that hosts a vast collection of machine learning datasets, covering diverse domains and tasks. This function allows you to easily download and prepare these datasets for use in your machine learning projects. Inputs. Name the name or identifier of the dataset you want to fetch from OpenML. This can be a dataset ID, a dataset name, or a URL to the dataset page. If you provide a name, FetchOpenML will attempt to find the dataset based on its name. If you provide a dataset ID, it will directly fetch the dataset with that ID. A URL will allow you to fetch the dataset from a specific location on OpenML. Version. The version of the dataset you want to retrieve. If not provided, the latest version will be fetched. Data home. The directory where the downloaded dataset will be stored. By default, it's stored in scikit-learn data as frame. Whether to return the dataset as a pandas data frame. If set to true, the returned object will be a data frame. Otherwise, it will be a NumPy array. Parser. The parser to use for loading the data. The default is auto, which attempts to infer the appropriate parser based on the dataset format. You can also specify parsers like pandas, LIAC-ARFF, or AutoGluon. Cache. Whether to cache the downloaded dataset locally. By default, it's set to true, which allows you to avoid re-downloading the dataset repeatedly. Download on request. If false, the dataset won't be downloaded immediately. Instead, it will be downloaded only when you access its attributes like data target or DESCR. Outputs. Dataset. A dictionary containing various attributes of the fetched dataset. This dictionary includes data, the dataset features or independent variables, typically as a NumPy array or a pandas data frame. Target. The dataset labels or dependent variables, typically as a NumPy array or a pandas series. DESCR. A description of the dataset, often including details about its source, task, features, and target variable. Feature names. Names or labels of the dataset features. Target names. Names or labels of the dataset target variable. Categorical features. A list of indices representing categorical features. Details. Additional metadata about the dataset from OpenML. Downloaded data path. The path where the dataset was downloaded and stored locally. Steps. Determine dataset. The function first determines the dataset to be fetched based on the provided input parameters. It uses the name, version, and data home to locate the dataset. Download and load if the dataset isn't already cached locally. FetchOpenML downloads the dataset from OpenML and stores it in the specified data home directory. It then loads the dataset into memory. Data preprocessing. The function performs basic preprocessing steps on the loaded dataset. These may include converting data types, handling missing values, and potentially encoding categorical features. Return output. Finally, FetchOpenML returns the processed dataset as a dictionary containing data, target, descriptions, and other relevant attributes. Metrics. Accuracy. This metric measures the proportion of correctly classified instances in a classification task. Precision. This metric calculates the proportion of correctly predicted positive instances among all instances predicted as positive. Recall. This metric calculates the proportion of correctly predicted positive instances among all actual positive instances. F1 score. This metric combines precision and recall into a single value, representing a harmonic mean of the two. Mean absolute error. This metric measures the average absolute difference between predicted and actual values in a regression task. Mean squared error. MSE. This metric measures the average squared difference between the predicted and actual values in a regression task. R squared. This metric represents the proportion of variance in the dependent variable that is explained by the independent variables in a regression task. Visualization plots. Scatter plot. A scatter plot is useful for visualizing relationships between two continuous variables. Histogram. A histogram is used to represent the distribution of a single continuous variable. Box plot. A box plot displays the distribution of a variable, highlighting quartiles, median, and outliers. Heat map. A heat map can visualize correlations between variables, represented by colors indicating strength and direction of relationships. Pair plot. A pair plot shows pairwise relationships between all variables in a dataset, offering a comprehensive view of data structure. Fine-tune parameters. Name. The name or identifier of the dataset to fetch. Version. The specific version of the dataset to download. Data home. The directory where the downloaded dataset is stored. As frame. Whether to return the dataset as a pandas data frame. Parser. The parser used for loading the data. Cache. Whether to cache the downloaded dataset locally. Download on request. Whether to download the dataset immediately or only when accessing its attributes. Uncertainty methods. Confidence intervals. Confidence intervals provide a range of values within which the true population parameter is likely to fall. Bayesian inference. This approach provides a framework for incorporating prior beliefs and updating them based on observed data to estimate uncertainty. Bootstrapping. This method involves resampling the original data with replacement to create multiple datasets, from which we can estimate uncertainty measures. Challenges and fixes. Challenge 1. Data format incompatibility. Some datasets may be in formats that are not directly compatible with scikit-learn's data processing functions. Sample use case that resulted in challenge 1. A dataset with a custom delimiter or a non-standard data format may lead to parsing errors. Fixes to challenge 1. Specify a custom parser using the parser parameter in FetchOpenML. You can use parsers like LIAC ARFF, AutoGluon, or a custom parser function. Manually preprocess the data before using it with scikit-learn. This may involve converting data types, handling missing values, or transforming features using techniques like one-hot encoding. Challenge 2. Missing data. Datasets may contain missing values, which can pose challenges for machine learning algorithms. Sample use case that resulted in challenge 2. A dataset with missing values in some features might lead to errors during model training. Fixes to challenge 2. Use techniques like imputation to fill in missing values. Common imputation methods include mean-median imputation, k-nearest neighbors imputation, and model-based imputation. Remove rows or columns with missing values if the missing data is extensive or if removing them doesn't significantly affect the analysis. Consider using machine learning models that can handle missing data directly, such as decision trees or random forests. Challenge 3. Large dataset size. Downloading and processing large datasets can consume significant time and resources. Sample use case that resulted in Challenge 3. A dataset with millions of instances and hundreds of features might be challenging to download, load, and process. Fixes to Challenge 3. Use the download on request parameter to delay the download until you actually need to access the data. This can save time if you only need to work with a subset of the dataset. Consider using a data streaming library like Dask to handle large datasets efficiently. Perform data preprocessing on a smaller sample of the dataset to optimize parameters and techniques before processing the full dataset. sklearn, datasets, fetch RCV1. Description. Inputs. None. Dataset: a dictionary-like object containing the RCV1 dataset. Dataset: data: a sparse matrix of shape 804414. 47,236 representing the features of the dataset. Each row corresponds to a document, and each column corresponds to a word. The values in the matrix represent the term frequency inverse document frequency TF-IDF scores of each word in each document. Dataset: target: an array of shape 804414, containing the labels for each document. The labels are integers representing the different topics that the documents belong to. Dataset: DESCR: a string describing the dataset. Dataset: file names: a list of strings containing the file names of the documents. Steps: the dataset is downloaded from the RCV1 website. The dataset is parsed and converted into a format that can be used by scikit-learn. The dataset is split into features and labels. The features are converted into a sparse matrix. Metrics: none. Visualization plots: none, none, none. Challenge 1: the dataset is very large and can take a long time to download and process. Sample use case that resulted in Challenge 1: trying to load the entire dataset into memory on a machine with limited RAM. Fixes to Challenge 1: use a sparse matrix format to store the data. Download the dataset in chunks. Challenge 2: the dataset is highly imbalanced, with some topics having many more documents than others. Sample use case that resulted in Challenge 2: training a classifier on the dataset and finding that it performs poorly on some of the minority topics. Fixes to Challenge 2: use oversampling or undersampling techniques to balance the dataset. Challenge 3: the dataset contains many words that are not relevant to the topics, which can make it difficult to train a classifier that performs well. Sample use case that resulted in Challenge 3: training a classifier on the dataset and finding that it performs poorly on some of the topics, even after balancing the dataset. Fixes to Challenge 3: use feature selection techniques to identify and remove irrelevant features. Challenge 4: the dataset is in English, which can be a problem if you need to use it for a different language. Sample use case that resulted in Challenge 4: trying to use the dataset for a French language text classification task. Fixes to Challenge 4: translate the dataset into the target language. Challenge 5: the dataset is not pre-processed, which can make it difficult to use with some machine learning algorithms. Sample use case that resulted in Challenge 5: trying to use the dataset with a machine learning algorithm that requires pre-processed data, such as a neural network. Fixes to challenge 5 pre-process the dataset using techniques such as stemming, lemmatization, and stop word removal. Challenge 6 the dataset is not in a standard format, which can make it difficult to use with other machine learning libraries. Sample use case that resulted in challenge 6 trying to use the dataset with a machine learning library that expects a different format, such as PTorch. Fixes to challenge 6 convert the dataset into the desired format. sklearn, datasets, fetch species distributions. Description. This function loads data for the ecological niche modeling (ENM) problem of predicting the geographic distribution of species based on environmental data. Inputs. Species a string specifying the species for which to retrieve data. Download if missing a boolean indicating whether to download the data if it is not already present. Locally. Return C a boolean indicating whether to return the data as a tuple of features X and labels Y, or as a dictionary with additional metadata. Sframe a boolean indicating whether to return the data as pandas data frames. Data home a string specifying the directory where the data should be stored. Outputs. Data a dictionary containing the following keys. Data a NumPy array containing the environmental data for each grid cell. Target a NumPy array containing the presence-absence labels for each grid cell. Samples a dictionary containing information about the species and the data. Feature names a list of strings describing the environmental variables X, Y a tuple containing the features X and labels Y if return C is true. Steps. Load data from a specified species from the GBIF database and corresponding environmental data from the WorldClum database. The data is then preprocessed to create a grid of data points. Metrics. Accuracy. This metric evaluates the model's ability to correctly predict the presence or absence of a species in a given location. Precision measures the model's ability to correctly identify true positives, i.e., the number of correctly predicted presences divided by the total number of predicted presences. Recall this metric measures the model's ability to correctly identify true positives, i.e., the number of correctly predicted presences divided by the total number of actual presences. F1 score. This metric combines precision and recall to provide a balanced evaluation of the model's performance. Visualization plots. Presence-absence map. A map displaying the locations where the species has been observed presence and where it has not been observed absence. Environmental variable maps. Maps showing the distribution of different environmental variables, such as temperature, precipitation, and elevation. Fine-tune parameters. Model selection. Choosing the appropriate machine learning model for the specific problem, such as a random forest, support vector machine, or boosted tree. Feature engineering. Selecting, transforming, and creating new features that improve the model's performance. Hyperparameter tuning. Optimizing the model's parameters to achieve the best performance on given data. Uncertainty methods. Ensemble methods using multiple models to predict the distribution and quantify uncertainty. Bayesian methods. Employing Bayesian statistics to quantify uncertainty in the model's predictions. Challenges and fixes. Challenge 1. Data imbalance. The dataset may contain a large number of grid cells with absence labels and a relatively small number of grid cells with presence labels. Sample use case that resulted in challenge 1. The dataset for a particular species might have a large number of grid cells with no observations. making it difficult to train a model effectively. Fixes to challenge 1. Undersampling, removing some of the absence labels to create a more balanced dataset. Oversampling, duplicating some of the presence labels to increase the number of positive samples. Synthetic minority oversampling technique, smooth generating synthetic samples of the minority class presence to balance the dataset. Challenge 2. Spatial autocorrelation, the presence of a species in one location might be correlated with its presence in nearby locations. Sample use case that resulted in challenge 2. A species might be more likely to be found in areas with similar environmental conditions, which can lead to spatial autocorrelation in the data. Fixes to challenge 2. Incorporate spatial information, using spatial information in the model to account for the correlation between locations. Spatial cross-validation, using spatial cross-validation to evaluate the model's performance in a way that accounts for spatial autocorrelation. sklearn, datasets, get data home. Description. Inputs. None. The path to the scikit-learn data directory. Steps. If the DATADIR environment variable is set, it will use that path. Otherwise, it will use the default data directory, which is scikit-learn data on Unix-like systems. CUSERSUSERSCIKIT-learn data on Windows. Metrics. None. Visualization plots. None. 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 Challenge 1. Data directory does not exist. Sample use case that resulted in challenge 1 the first time using scikit-learn datasets on a new machine. Fixes to challenge 1. The getDataHome function will automatically create the directory if it does not exist. Challenge 2. Data directory is not writable. Sample use case that resulted in challenge 2. The user does not have write permissions to the default data directory. Fixes to challenge 2. Set the DATADIR environment variable to a writable directory. Run the code as a user with write permissions to the default data directory. Challenge 3. Data directory is too small. Sample use case that resulted in challenge 3. The user is trying to download a large dataset and the data directory is full. Fixes to challenge 3. Delete old datasets to free up space. Set the DATADIR environment variable to a directory with more space. sklearn, datasets, load breast cancer. Description. This function loads the breast cancer Wisconsin diagnostic dataset from the UCI machine learning repository. The dataset contains features computed from digitized images of fine needle aspirates of a breast mass. These features are used to predict whether a tumor is malignant or benign. Inputs. None. Outputs. Data a NumPy array of shape 569. 30 representing the 30 features for each of the 569 samples. Target a NumPy array of shape 569. Representing the class labels 0 for benign, 1 for malignant. Frame a pandas data frame containing the data, target, and other information. DESCR a string describing the dataset. Feature names a list of length 30 containing the names of the features. Target names a list of length 2 containing the names of the target classes. File name the path to the CSV file containing the data. Steps. Load the dataset. The function downloads and loads the dataset from the UCI machine learning repository. Preprocess the data. The data is preprocessed to handle missing values and convert categorical features to numerical features. Return the dataset. The function returns a dictionary containing the data, target, and other information. Metrics: accuracy percentage of correctly classified samples. Precision proportion of correctly predicted positive samples among all predicted positive samples. Recall proportion of correctly predicted positive samples among all actual positive samples. F1 score harmonic mean of precision and recall. Visualization plots. Scatter plot to visualize the relationship between different features. Heat map to visualize the correlation between different features. Principal component analysis PCA plot to visualize the data in a lower dimensional space. Fine-tune parameters. None. Uncertainty methods. Confidence intervals to quantify the uncertainty in the model's predictions. Bayesian inference to estimate the posterior distribution of the model's parameters. Challenges and fixes. Challenge 1: class imbalance. The dataset has a significant class imbalance, with more benign samples than malignant samples. Sample use case that resulted in challenge 1: a model trained on this dataset might be biased towards predicting benign tumors, leading to poor performance on malignant tumors. Fixes to challenge 1: oversampling, replicating minority class samples to balance the dataset. Undersampling, removing majority class samples to balance the dataset. Cost-sensitive learning, assigning higher weights to minority class samples during training. Challenge 2: feature scaling. The features have different scales, which can affect the performance of some machine learning models. Sample use case that resulted in challenge 2: a model trained on unscaled features might be biased towards features with larger scales, leading to poor performance. Fixes to challenge 2: standardization, rescaling the features to have zero mean and unit variance. Normalization, rescaling the features to have a range between 0 and 1. Feature engineering, creating new features that are more informative or have more appropriate scales. Challenge 3: data dimensionality. The dataset has 30 features, which can make it difficult to train some machine learning models and interpret the results. Sample use case that resulted in challenge 3: a model trained on all 30 features might be overfitting the data, leading to poor generalization performance. Fixes to challenge 3: feature selection, selecting a subset of the most informative features. Dimensionality reduction, reducing the number of features using techniques such as PCA. Regularization, adding penalties to the model's parameters to prevent overfitting. Challenge 4: overfitting. The model might overfit the training data, leading to poor generalization performance. Sample use case that resulted in challenge 4: a model with too many parameters or trained for too long might overfit the training data, resulting in poor performance on unseen data. Fixes to challenge 4: cross-validation, splitting the data into training and validation sets to evaluate the models performance on unseen data. Early stopping the training process when the model's performance on the validation set starts to degrade. Regularization, adding penalties to the model's parameters to prevent overfitting. Challenge 5: data leakage, using information from the test set during training can lead to unrealistic performance estimates. Sample use case that resulted in challenge 5: using the test set to select features or tune hyperparameters can lead to data leakage, resulting in overly optimistic performance estimates. Fixes to challenge 5: proper data splitting, ensure that the test set is not used during training or hyperparameter tuning. Cross-validation, using cross-validation to evaluate the model's performance on unseen data. sklearn, datasets, load diabetes. Description: the diabetes dataset contains 442 instances with 10 features each, describing patients with diabetes. The goal is to predict the disease progression 1 year after the baseline. Inputs: None. Outputs. Dataset a dictionary-like object with the following keys. Data a NumPy array of shape 442. 10 containing the 10 features for each patient. Target a NumPy array of shape 442. Containing the disease progression 1 year after baseline. DESCR a string describing the dataset. Feature names a list of strings containing the names of the 10 features. Data file name a string indicating the path to the data file. Target file name a string indicating the path to the target file. Steps. The dataset is loaded from the scikit-learn library. The data is read and stored in a dictionary-like object. Metrics. Mean squared error MSE commonly used to evaluate regression models. Measuring the average squared difference between predicted and actual values. R squared R2 indicates the proportion of variance in the target variable that is explained by the model. Visualization plots. Scatter plots to visualize the relationship between each feature and the target variable. Pair plots to visualize the relationships between all pairs of features. Fine-tune parameters. Regularization techniques like L1 or L2 regularization can be used to prevent overfitting by penalizing large coefficients. Feature selection techniques like feature importance or recursive feature elimination can be used to select the most relevant features. Uncertainty methods. Confidence intervals can be used to quantify the uncertainty in the model's predictions. Bootstrapping a resampling technique that can be used to estimate the uncertainty in model. Parameters. Challenges and fixes. Overfitting the model might overfit the training data and fail to generalize to unseen data. Sample use case. A model trained on a small dataset might learn the noise in the data, leading to poor performance on new data. Fixes. Use regularization techniques to prevent overfitting. Increase the size of the training dataset. Feature scaling. Features with different scales can affect the performance of the model. Sample use case. Features like age and blood pressure have vastly different scales. This can cause some features to have a disproportionate influence on the model. Fixes. Apply feature scaling techniques like standardization or normalization to bring all features to a similar scale. sklearn. Datasets. Low-digits. Description. The low-digits function from scikit-learn's datasets module provides a dataset containing 1797 8x8 grayscale images of handwritten digits. Each image represents a digit from 0 to 9. It is a commonly used dataset for exploring classification tasks with machine learning algorithms. Inputs. None. The function does not require any specific inputs. Outputs. Dataset. This is a dictionary-like object containing the dataset's information. It includes data an array of shape 1797. 64 representing the pixel values of each image, flattened into 64 values. Target an array of shape 1797, containing the corresponding digit label for each image. Target names a list of strings representing the possible digit labels 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. DESCR a string containing a description of the dataset. Images an array of shape 1797. 8. 8 representing the actual 8x8 pixel images. Images optional if return xy true is passed to the function. It will return a tuple containing the data and target arrays separately. Steps. The function retrieves the dataset from its source, likely a built-in file or a remote repository. It parses the data and labels, storing them into the appropriate arrays. It returns the dataset dictionary or a tuple of data and target arrays, depending on the return C argument. Metrics, not specifically provided by the function itself, but common metrics for evaluating digit classification models include accuracy, the proportion of correctly classified digits; precision, the proportion of correctly classified digits among all predicted digits for a specific class; recall, the proportion of correctly classified digits among all actual instances of a specific class; F1 score, a harmonic mean of precision and recall; visualization plots, scatter plot, visualizing the data points using the pixel values as features can reveal clusters corresponding to different digits; confusion matrix, a matrix showing the frequency of correct and incorrect classifications for each digit; image grid, displaying a grid of images with their corresponding labels can provide a visual understanding of the dataset; fine-tune parameters, return, see a Boolean value default false that determines whether the function returns a dictionary with all dataset information or a tuple containing only the data and target arrays; uncertainty methods, not specifically related to low digits itself. However, uncertainty estimation methods for machine learning models trained on this dataset could include Bayesian inference, using probabilistic models to estimate the uncertainty of predictions; dropout, a technique for regularizing neural networks and estimating uncertainty by randomly dropping out neurons during training; challenges and fixes. Challenge 1, data imbalance, some digits may be more frequent in the dataset than others, potentially causing a bias in the trained model. Sample use case that resulted in challenge 1, a model trained on low digits may perform poorly on recognizing less frequent digits, especially if the training data distribution is not representative of real-world data. Fixes to challenge 1. Data augmentation, generate synthetic samples of less frequent digits using techniques like rotations, translations, or image distortions. Class weights, assign higher weights to less frequent digits during training to balance their contribution to the model's loss function. Challenge 2, limited data, the dataset contains only 1797 samples, which may not be sufficient to train highly complex models. Sample use case that resulted in challenge 2, training a deep neural network on low digits may lead to overfitting, as the model learns the specific characteristics of the training data too closely. Fixes to challenge 2. Use a simpler model, choose a model with fewer parameters or a less complex architecture. Regularization, apply techniques like dropout, weight decay, or L1-L2 regularization to prevent overfitting. Data augmentation, generate synthetic data from existing samples to increase the dataset size. YAML, sklearn, datasets, load files. Description. The load files function in scikit-learn is a utility for loading datasets consisting of text documents organized into subfolders, each subfolder representing a distinct class or category. It's a handy tool for text classification tasks where you have a collection of documents categorized by their subject matter. Inputs. Dataset dir, the path to the directory containing the subfolders with your text documents. Description, an optional string describing the dataset. Categories, an optional list of categories to load. If not provided, all categories will be loaded. Load content, a Boolean indicating whether to load the content of the files. Default is true. Shuffle, a Boolean indicating whether to shuffle the dataset. Default is true. Random state, an integer, random state instance or none default used for shuffling the data. Encoding, the encoding used to read the text files. Default is UTF-8. Outputs. Data, a NumPy array containing the text data of each document, represented as strings. Target a NumPy array containing the integer labels for each document corresponding to the category. Target names a list of the category names. DESCR a string describing the dataset. File names a list of the file names of the documents. Steps. The function first reads the directory structure and identifies the subfolders representing different categories. It then iterates through each category folder, reading the text files within. The content of each file is loaded if load content true, and the file name is stored. The data. Target labels representing categories, file names, and category names are organized into the output format. Metrics. Accuracy a common metric for evaluating classification models, measuring the percentage of correctly classified instances. Precision the ratio of correctly predicted positive instances to the total number of predicted positive instances. Recall the ratio of correctly predicted positive instances to the total number of actual positive instances. F1 score a harmonic mean of precision and recall. Visualization plots. Confusion matrix a visualization showing the distribution of predicted and actual classes, highlighting misclassifications. ROC curve a plot showing the trade-off between true positive rate and false positive rate for different classification thresholds. Word cloud a visualization representing the frequency of words in the dataset, providing insights into the topic distribution. Fine-tune parameters. Categories selecting specific categories to load allows you to focus on relevant data for your task. Shuffling the dataset helps to ensure that your model doesn't learn patterns based on the order of the data. Uncertainty methods. Confidence intervals using methods like bootstrapping to estimate the uncertainty around your model's predictions. Bayesian inference incorporating prior knowledge into your model to capture uncertainty in the data. Challenges and fixes. Challenge 1 imbalanced datasets if some categories have significantly fewer documents than others. Your model may struggle to learn patterns for the smaller categories. Sample use case a dataset of movie reviews where 90 are positive and 10 are negative. Fixes. Oversampling creating synthetic instances of the minority class. Undersampling removing instances from the majority class. Class weighing adjusting the loss function to give more importance to minority class examples. Challenge 2 text preprocessing raw text often contains irrelevant information like stop words, punctuation, and capitalization. Preprocessing can improve the performance of your model. Sample use case a dataset with many misspelled words or inconsistent capitalization. Fixes. Stop word removal removing common words that don't provide much meaning. Stemming reducing words to their root form. Lemmatization converting words to their dictionary form. Lowercasing converting all text to lowercase. Challenge 3 feature extraction representing text data in a way that's suitable for machine learning algorithms is crucial. Sample use case using a dataset with long, complex documents that are difficult to represent directly. Fixes. Bag of words bow representing text as a vector where each dimension corresponds to a word in the vocabulary. TF-IDF weighing words based on their frequency within a document and across the entire dataset. Word embeddings representing words as dense vectors, capturing semantic relationships between words. sklearn, datasets, load iris. Description: the load iris function in scikit-learn sklearn provides access to the iris dataset, a classic dataset in machine learning used for classification tasks. The dataset contains measurements of 150 iris flowers from 3 species Setosa, versicolor, and virginica. Inputs. None. The load iris function does not take any input parameters. Outputs. Data. A NumPy array of shape 150. 4 containing the measurements for each flower. The features are sepal length, sepal width, petal length, and petal width. Target. A NumPy array of shape 150. Containing the species label for each flower 0 Setosa, 1 versicolor, 2 virginica. Frame. A pandas data frame containing the data and target, with columns named sepal length cm, sepal width cm, petal length cm, petal width cm, and target. Description. A dictionary containing information about the dataset, including the feature names, the target names, and the source of the data. Steps. Load the iris dataset from a local file or a remote server. Create a NumPy array for the data and a NumPy array for the target. Create a pandas data frame to store the data and target. Create a dictionary with information about the dataset. Metrics. Accuracy measures the percentage of correctly classified samples. Precision measures the proportion of correctly predicted positive instances out of all predicted positive instances. Recall measures the proportion of correctly predicted positive instances out of all actual positive instances. F1 score. The harmonic mean of precision and recall. Visualization plots. Scatter plots visualize the relationships between different features. For example, sepal length vs. sepal width. Pair plots show the relationships between all pairs of features in the dataset. Box plots display the distribution of each feature for each species. Fine-tune parameters. None. The load iris function does not have any tunable parameters. Uncertainty methods. None. The load iris function does not directly address uncertainty methods. Challenges and fixes. Challenge 1. The iris dataset is relatively small, which can limit the performance of complex machine learning models. Sample use case that resulted in challenge 1. A deep learning model trained on the iris dataset may not generalize well to new data. Fixes to challenge 1. Use data augmentation techniques to increase the size of the dataset or explore alternative datasets with more samples. Challenge 2. The iris dataset is balanced, meaning that each species has an equal number of samples. This can make it difficult to evaluate the performance of models that are sensitive to class imbalance. Sample use case that resulted in challenge 2. A model that predicts the species of a flower might perform well on the iris dataset but poorly on a dataset with an imbalanced distribution of species. Fixes to challenge 2. Resample the data to create a balanced dataset or use a cost-sensitive learning approach to account for class imbalance. sklearn. Datasets. LoadLeNerd. Description. The loadLeNerd function loads the leNerd dataset, a classic dataset used in multivariate statistics to explore relationships between physical attributes and exercise performance. The dataset contains data on 20 individuals, including their physical attributes: age, weight, height, resting pulse, maximum pulse, and running time for 1.5 miles, and their performance on 3 exercise tests: chins, sit-ups, and jumps. Inputs. None. This function does not take any inputs. Data. A NumPy array of shape 23, containing the exercise test results: chins, sit-ups, jumps for each individual. Feature names. A list of strings, providing the names of the 3 exercise tests: chins, sit-ups, jumps. Target. A NumPy array of shape 20. 6. Containing the physical attributes age, weight, height, resting pulse, maximum pulse, running time for each individual. DESCR a string describing the Linode dataset, including its source, motivation, and the meaning of each variable. Frame a pandas data frame containing all the data, with column names matching the feature names in the attributes. Steps. Load the data. The function retrieves the dataset from its internal storage. Format the data. The function formats the data into the desired output structure NumPy arrays. List of strings. Pandas data frame. Assign descriptive attributes. The function assigns attributes like feature names, DESCR, and frame to provide context and details about the dataset. Metrics. No specific metrics are associated with the dataset itself. However, you can use various metrics when applying machine learning models to analyze the relationships between physical attributes and exercise performance. Examples include correlation coefficients, regression metrics R-squared, mean squared error, and classification metrics accuracy, precision, recall, visualization plots, scatter plots visualizing the relationships between physical attributes and exercise performance. Using scatter plots can reveal potential correlations. Box plots examining box plots of exercise performance across different age groups or weight categories can reveal potential differences in performance based on these factors. Principal component analysis PCA. Applying PCA to the data can help identify the principal components, linear combinations of variables that capture most of the variance in the dataset. Visualizing the data in the PCA space can reveal clusters or patterns in the data. Not applicable. This function does not involve any parameters to fine-tune. Bootstrapping. You can use bootstrapping techniques to assess the uncertainty in your models. Predictions. By repeatedly sampling the data with replacement and training the model on each resampled dataset, you can get an estimate of the variability in the predictions. Bayesian methods. Bayesian approaches allow you to incorporate prior beliefs about relationships between variables and obtain posterior distributions for model parameters, providing estimates of uncertainty. Challenge 1. The dataset is relatively small, with only 20 individuals. This can limit the generalizability of models trained on this dataset. Sample use case that resulted in challenge 1. A model trained on this dataset might not perform well on a larger, more diverse dataset. Fixes to challenge 1. Use cross-validation techniques to assess the model's performance on different subsets of the data, which can help to mitigate the effect of small sample size. Consider combining the Linode dataset with other similar datasets to increase the sample size. Challenge 2. The dataset may contain missing values or outliers, which could affect the performance of machine learning models. Sample use case that resulted in challenge 2. Missing values or outliers might lead to biased or inaccurate model predictions. Fixes to challenge 2. Implement data preprocessing steps such as imputation, filling in missing values, or outlier removal to address these issues. sklearn. Datasets. Load sample image. Description. Image name. The name of the image file to load. This is a string. Image. The loaded image. This is a NumPy array. The function loads the specified image file from the sklearn datasets module's data directory. The image is returned as a NumPy array with the shape, height, width, channels, none. The loaded image can be visualized using matplotlib. None. sklearn datasets load sample images. Description. The loadSampleImages function from scikit-learn is a utility function that loads a set of 3 sample images for use in various machine learning tasks. These images are included in the scikit-learn package and provide a convenient starting point for experimentation. Inputs. None. This function doesn't take any input parameters. It directly loads the predefined sample images. Outputs. Images. A list of 3 NumPy arrays, each representing a single image. The images are in color RGB format and are stored as unsigned 8-bit integers. The shape of each array is height, width. 3. Dataset. The function also returns a bunch object containing additional information about the dataset, including the description of the images and their file names. Steps. Loading. The function internally accesses the predefined image files from the scikit-learn package. Conversion. The images are loaded as NumPy arrays and their pixel values are represented as unsigned 8-bit integers. Metrics. None. The function doesn't directly compute any metrics related to the images. Metrics like image quality or specific characteristics would need to be calculated separately based on the loaded images. Visualization plots. Displaying the images. The loaded images can be visualized using libraries like Matplotlib, pyplot, to display them as plots. Fine-tune parameters. None. There are no parameters to fine-tune within the loadSampleImages function itself. Uncertainty methods. None. This function doesn't provide any uncertainty measures for the loaded images. Uncertainty analysis would require additional techniques and algorithms applied after loading the images. Challenges and fixes. Challenge 1. Unexpected image format. In certain cases, the loaded image might be in a format different from the expected RGB format, e.g., grayscale or a different color space. Sample use case that resulted in challenge 1. If the image data was generated from an external source and incorrectly processed, it might lead to unexpected image formats. Fixes to challenge 1. Convert the image to RGB format using libraries like OpenCV or PILPillow. Challenge 2. Image data corruption. The image data might be corrupted during loading or storage, resulting in missing or incorrect pixel values. Sample use case that resulted in challenge 2. If the image files are not properly stored or are affected by errors during file operations, corruption can occur. Fixes to challenge 2. Verify the image file integrity and ensure proper storage. Consider using robust file handling mechanisms to prevent data corruption. sklearn, datasets, loadsVMLite file. Description. The loadsVMLite file function loads data from a file in the svmlite.lib svm format. This format is commonly used for storing sparse data, particularly for machine learning tasks. Especially for classification and regression problems, the function reads the data and returns it as a NumPy array representing features, and a separate array containing the corresponding target values. Inputs. File the path to the file containing the data in svmlite.lib svm format. D-type data type for the features default float 64. 0 based whether the indices in the file are 0 based default true. Multilabel whether the dataset is multilabel. N features the number of features, if known. Outputs. X a NumPy array containing the features. Y a NumPy array containing the target values. Steps. The function reads the file line by line, parsing each line to extract the feature indices and their corresponding values, as well as the target value. It constructs the feature matrix X, where each row represents a data point, and each column corresponds to a feature. Since the data is sparse, only the non-zero values are stored. creating a sparse matrix representation. It creates the target vector Y, where each element corresponds to the target value of the corresponding data point. Metrics: none. Visualization plots: none. Fine-tune parameters: none. Uncertainty methods: none. Challenges and fixes. Challenge 1 file format inconsistencies. Sometimes the svm-lite-lib svm file may have minor deviations from the expected format, such as inconsistent delimiters or unexpected characters. Sample use case that resulted in challenge 1: a file with commas instead of spaces is delimiters. Fixes to challenge 1: modify the delimiter parameter in the loads_vm-lite file function to match the actual delimiter used in the file. Challenge 2: handling missing values. svm-lite-lib svm format does not explicitly represent missing values. The function assumes that missing values are simply not present in the data. Sample use case that resulted in challenge 2: a file where some features are missing for certain data points. Fixes to challenge 2: impute the missing values using suitable imputation techniques, e.g. mean imputation, median imputation before loading the data. Challenge 3: handling large datasets. Loading very large svm-lite-lib svm files can be memory intensive. Sample use case that resulted in challenge 3: a file containing millions of data points. Fixes to challenge 3: consider using a streaming approach to read the data in chunks, processing each chunk individually and avoiding loading the entire dataset into memory at once. This can be achieved using libraries like Dask or Pandas. sklearn, datasets, loads VM-lite files. Description: this function loads datasets in the svm-lite-lib svm format, which is a sparse format widely used for storing data for machine learning tasks, particularly for support vector machines SVMs. Inputs: files, a string or a sequence of strings, representing the paths to the files containing the dataset. If a string is provided, it's assumed to be a single file containing both the training and testing data. If a sequence is provided, it should contain pairs of training file, testing file strings. D-type the data type for the features and target values. Defaults to float 64. Multilabel if true. Loads the target values as a list of labels for each instance. Defaults to false. Zero-based if true. Assumes that the indices in the files are zero-based. Defaults to true. Queried if true. Returns an array of query IDs for each sample. Defaults to false. Offset a number to add to the feature indices in the files. Defaults to 0. Outputs: dataset, a dictionary containing the following keys. Data, a sparse matrix containing the features. Target, an array containing the target values. DESCR, a string describing the dataset. Feature names, an array containing the feature names. This is only available if the file contains feature names. Queried, an array of query IDs for each sample. This is only available if the queried parameter is set to true. Datasets, a list of dictionaries, each containing the same keys as the dataset dictionary. This is returned if the file's parameter is a sequence. Steps: the function reads the contents of the files provided in the file's parameter. It parses the data and extracts the features, target values, and optionally, feature names and query IDs. The function creates a sparse matrix to store the features and an array to store the target values. It returns a dictionary or a list of dictionaries containing the extracted data. Metrics: not directly applicable to the function itself. It's used to load data, so the metrics would be applied to the models trained on the loaded data. Visualization plots: not directly applicable to the function itself. It's used to load data. So the plots would be generated from the data loaded using the function. Fine-tune parameters. dtype adjust the data type of the features and target values based on the datasets, characteristics and the requirements of the machine learning model. Multilabel set to true if the dataset contains multiple labels for each instance. Otherwise, keep it as false. Zero-based adjust based on the indexing convention used in the svm-lightlib svm files. Queried set to true if the files contain query IDs. Otherwise, keep it as false. Offset use this parameter to adjust the feature indices if necessary. Uncertainty methods, not directly applicable to the function itself. It's used to load data. So the uncertainty methods would be applied to the models trained on the loaded data. Challenges and fixes. Challenge 1 File format issues. Sample use case encountering issues loading files with incorrect format, missing headers, or unexpected data structures. Fixes. Carefully inspect the format of the svm-lightlib svm files to ensure they adhere to the expected structure. Verify that the header line is present and properly formatted. Use a text editor or a specialized tool to examine the file contents and identify potential errors. Challenge 2 Memory management. Sample use case loading large datasets into memory may lead to memory exhaustion. Fixes. Consider using a sparse matrix representation for storing the data to reduce memory consumption. Explore alternative data loading methods, like loading data in batches or using streaming libraries. Adjust the dtype parameter to use smaller data types if possible, without sacrificing precision. Challenge 3 Feature scaling and transformation. Sample use case the loaded features might not be in a suitable range for some machine learning algorithms. Fixes. Consider applying feature scaling techniques like standardization or normalization before training the model. Use the appropriate preprocessing methods provided by scikit-learn, such as standard scaler or min-max scaler. Experiment with different feature transformation techniques to find the best approach for the specific dataset and model. sklearn, datasets, loadwine. Description. The loadwine function in scikit-learn provides a dataset containing information about various chemical properties of wines grown in the same region in Italy but derived from 3 different cultivars. The goal of this dataset is to classify the wine based on its chemical properties. Inputs. None. The function takes no inputs. It directly loads the predefined dataset from scikit-learn's resources. Outputs. Dataset a dictionary-like object containing the following attributes. Data a NumPy array of shape 178. 13 representing the chemical properties of the wines, with 178 samples and 13 features. Target a NumPy array of shape 178, representing the class labels for each wine, with values ranging from 0 to 2 corresponding to the 3 cultivars. Frame a pandas data frame containing the data and target information. Target names a list of strings representing the names of the 3 cultivars class 0, class 1, and class 2. DESCR a string describing the dataset, its origin, and its features. Feature names a list of strings representing the names of the 13 features in the dataset. Target a NumPy array representing the class labels for each wine. Steps. Load the predefined dataset from scikit-learn's resources. Extract the data, target, and other attributes from the dataset. Organize the data into a dictionary-like object for easy access. Metrics. Accuracy the percentage of correctly classified wines. Precision, the proportion of correctly classified samples among those predicted as belonging to a specific class. Recall, the proportion of correctly classified samples among all samples belonging to a specific class. F1 score, a harmonic mean of precision and recall, providing a balanced measure of performance. Visualization plots. Scatter plots visualize the relationship between different features in the dataset. Histograms examine the distribution of individual features. Pair plots create a matrix of scatter plots to visualize the relationships between all pairs of features. Principal component analysis PCA plots reduce the dimensionality of the data and visualize the separation between the classes in a lower dimensional space. Fine-tune parameters. None. The loadWine function does not provide any tunable parameters. It simply loads the predefined dataset. Uncertainty methods. None. The loadWine function does not provide any methods for assessing uncertainty. Challenges and fixes. Challenge 1: the dataset is relatively small, with only 178 samples, which might limit the performance of certain machine learning models. Sample use case that resulted in challenge 1 using a complex deep learning model on the dataset might result in overfitting due to the limited data size. Fixes to challenge 1. Use data augmentation techniques to generate synthetic samples from the existing data. Employ regularization techniques to prevent overfitting in models. Consider using ensemble methods to combine the predictions of multiple models. Challenge 2: the dataset is imbalanced, with a different number of samples for each cultivar. Sample use case that resulted in challenge 2 using a simple classification model without addressing the class imbalance might lead to biased predictions towards the majority class. Fixes to challenge 2. Use oversampling techniques to increase the number of samples in the minority classes. Employ undersampling techniques to reduce the number of samples in the majority class. Use cost-sensitive learning methods to assign different weights to different classes during training. sklearn datasets make biclusters. Description: this function generates a synthetic dataset with biclusters, which are submatrices with constant values. It's useful for testing and evaluating biclustering algorithms. Inputs: shape a tuple NROWS. NCOLS representing the desired dimensions of the generated dataset. N clusters, the number of biclusters to create in the dataset. Shuffle Boolean indicating whether to shuffle the rows and columns of the dataset after creation. This is useful for simulating real-world scenarios where data might not be perfectly ordered. Random state, an integer or none. Used for initializing the random number generator. This ensures reproducibility of the generated dataset. Outputs: data a 2D NumPy array representing the generated dataset with biclusters. Rows a 1D NumPy array indicating the row indices belonging to each bicluster. Columns a 1D NumPy array indicating the column indices belonging to each bicluster. Steps: the function first generates a matrix of random values with dimensions specified by the shape parameter. It then randomly selects n cluster submatrices biclusters within the matrix. For each bicluster, a constant value is chosen randomly. This value is assigned to all the cells within the corresponding submatrix. If shuffle is true, the rows and columns of the dataset are randomly shuffled after the biclusters are created. Metrics: the quality of the biclustering algorithm can be evaluated using metrics like silhouette score measures how well data points are clustered together based on their similarity to points within the same cluster and dissimilarity to points in other clusters. Kalinski-Haraba's score measures the ratio of between cluster variance to within cluster variance. Higher scores indicating better separation between clusters. Visualization plots. Heat map. A heat map can be used to visualize the generated dataset and highlight the biclusters as regions of constant color. Dendrogram. A dendrogram can be used to visualize the hierarchical structure of the data and pay relationships between the biclusters. Fine-tune parameters. Shape. Adjust the number of rows and columns in the dataset to simulate different real-world scenarios. N clusters control the number of biclusters present in the dataset. This parameter affects the complexity of the data and the difficulty of finding the biclusters. Uncertainty methods. Not applicable for this function, as it does not involve any probabilistic or uncertainty measures. Challenges and fixes. Challenge 1. Overlapping biclusters. Sample use case when creating a dataset with a high number of biclusters and a relatively small dataset size. The generated biclusters might overlap significantly. Fixes. Increase the dataset size shape parameter to reduce the overlap between biclusters. Adjust the number of biclusters N clusters parameter to create fewer, but larger and more distinct biclusters. Challenge 2. Noisy data. Sample use case. Real-world datasets often contain noise, which can make biclustering algorithms less effective. Fixes. Introduce random noise to the generated dataset to simulate real-world noise. Use biclustering algorithms that are robust to noise, such as spectral biclustering or Cheng-Church biclustering algorithm. sklearn. Datasets. Make blobs. Description. This function generates synthetic data clusters for use in machine learning tasks, particularly for testing and demonstrating clustering algorithms. Inputs. N samples the total number of data points to be generated. N features the number of features dimensions for each data point. Centers the number of centers to generate, or an array of shape N centers. N features representing the centers themselves. Clusters TD. The standard deviation of the clusters. It can be a single value, or a list array of length N centers. Outputs. X. An array of shape N samples. N features containing the generated data points. Y. An array of shape N samples, containing the cluster labels for each data point. Steps. The function first generates the cluster centers based on the centers parameter. For each data point, it randomly selects a cluster center. It then generates a random data point from a Gaussian distribution centered around the selected cluster center, with standard deviation specified by clusters TD. Finally, it assigns the corresponding cluster label to each generated data point. Metrics. Silhouette score. A metric to evaluate the quality of clustering, where a higher score indicates better separation between clusters. Davies-Bouldin index. Another metric for evaluating clustering quality, with a lower score indicating better separation. Visualization plots. Scatter plot. A 2D plot where each data point is colored according to its cluster label, visually representing the clustering structure. Pair plot. If the number of features is small, e.g., 2 or 3. A pair plot can show the pairwise relationships between features for each cluster. Fine-tune parameters. Clusters TD. By adjusting the standard deviation of the clusters, you can control the degree of overlap between them. Smaller values lead to tighter clusters with better separation. Random state setting. A specific value for random state ensures that the generated data remains consistent across different runs, making it easier for reproducibility. Uncertainty methods. Confidence intervals for each cluster center. You can calculate confidence intervals based on the distribution of points within the cluster. This helps assess the uncertainty in the estimated center location. Bayesian clustering. Some clustering algorithms incorporate Bayesian inference, allowing for uncertainty estimates in cluster assignments. Challenges and fixes. Challenge 1. Overlapping clusters. If the standard deviation of the clusters is large or centers are close together, the generated clusters may significantly overlap. Sample use case that resulted in challenge 1. When using clusters TD 2.0 with centers that are close together, the generated clusters might be too diffuse and hard to distinguish. Fixes to challenge 1. Reduce the cluster's TD value, or increase the distance between the cluster centers. Challenge 2. Imbalanced clusters. If the number of data points per cluster is uneven, some clusters might be underrepresented, leading to biases in the clustering analysis. Sample use case that resulted in challenge 2. Specifying a larger N samples value, but with very different numbers of samples assigned to each center, might create imbalanced clusters. Fixes to challenge 2. Ensure that the number of samples per cluster is balanced, or use a weighted clustering algorithm that accounts for imbalance. sklearn, datasets, make checkerboard. Description. The make checkerboard function generates a synthetic dataset that is a checkerboard pattern of two classes. This dataset is useful for testing classification algorithms that are sensitive to spatial patterns. Inputs. N samples, the number of samples to generate. N features, the number of features dimensions for each sample. Random state controls the shuffling applied to the dataset. Pass an int for reproducible output across multiple function calls. Shuffle, whether to shuffle the dataset or not. Outputs. X, the generated checkerboard data. An array of shape N samples. N features. Y, the corresponding labels 0 or 1 for each sample in X. Steps. Generate a grid of points with N features dimensions, where each dimension ranges from 0 to 1. Calculate the parity even or odd of each point along each dimension. Assign a label of 0 to points that have an even parity along all dimensions and a label of 1 to points that have an odd parity along any dimension. Shuffle the dataset if shuffle is set to true. Metrics. Accuracy, the percentage of samples that are correctly classified. Precision, the proportion of positive predictions that are actually positive. Recall, the proportion of positive samples that are correctly identified. F1 score, the harmonic mean of precision and recall. Visualization plots. Scatter plot of the data, where each point is colored according to its label. Decision boundary plot showing the regions where the classifier predicts each class. Fine-tune parameters. N samples, the number of samples to generate. Increasing this number can improve the performance of the classifier. N features, the number of features dimensions for each sample. Increasing this number can make the dataset more complex and challenging to classify. Uncertainty methods. Confidence intervals can be used to estimate the uncertainty in the predictions of the classifier. Bayesian inference can be used to incorporate prior knowledge about the data into the classifier. Challenges and fixes. Challenge 1. The dataset is very simple and can be easily classified by a linear classifier. Sample use case that resulted in challenge 1. A linear SVM classifier was trained on the dataset and achieved perfect accuracy. Fixes to challenge 1. Increase the number of features to make the dataset more complex. Add noise to the data to make it more realistic. Challenge 2. The dataset is very balanced, with an equal number of samples in each class. Sample use case that resulted in challenge 2. A classifier was trained on the dataset and achieved a high accuracy score. but it was biased towards the majority class. Fixes to challenge to use a balanced dataset with an equal number of samples in each class. Use a classifier that is less sensitive to class imbalance. sklearn datasets make circles. Description: this function generates a synthetic dataset consisting of two concentric circles with a specified number of points for each circle. It is commonly used for testing and evaluating machine learning algorithms designed for binary classification problems, as the dataset exhibits a clear nonlinear boundary between the two classes. Inputs: n samples, the total number of points to generate. This parameter determines the size of the dataset. Factor the ratio of the radius of the smaller circle to the radius of the larger circle. This parameter controls the separation between the circles. A smaller factor value results in tighter circles, making the classification task more challenging. Outputs: X, a NumPy array of shape n samples, 2 containing the coordinates of the generated points. Each row represents a data point with two features, x coordinate and y coordinate. Y, a NumPy array of shape n samples, containing the class labels for each point. Labels are either 0 for the points on the outer circle or 1 for the points on the inner circle. Steps: the function starts by generating a specified number of points for each circle, ensuring that the number of points for each circle is roughly equal. For each circle, the points are distributed uniformly on the circumference. The smaller circle is then scaled by the factor parameter, determining the relative size of the inner circle compared to the outer circle. Finally, the points from both circles are combined into a single dataset, and the corresponding class labels are assigned. Metrics: accuracy: this metric measures the percentage of correctly classified points. It is commonly used to evaluate the performance of binary classification models. Precision: this metric represents the proportion of correctly classified positive instances. Inner circle among all instances predicted as positive. Recall: this metric reflects the proportion of correctly classified positive instances inner circle among all actual positive instances. F1 score: this metric provides a balanced measure of precision and recall. Visualization plots. Scatter plot: a scatter plot can be used to visualize the generated dataset, where each point is plotted according to its x and y coordinates. The points belonging to different classes can be distinguished by color or marker style. Decision boundary plot for a trained classification model. The decision boundary can be visualized on the same scatter plot. The decision boundary represents the line or curve that separates the regions where the model predicts different classes. Fine-tune parameters. N samples: increasing the number of samples can make the dataset more representative and improve the model's generalization ability. However, it can also increase computation time. Factor adjusting: the factor parameter can change the difficulty of the classification task. A smaller factor value results in tighter circles, making the classification task more challenging. Noise: this parameter controls the amount of random noise added to the data points. Increasing the noise can make the classification task more difficult. Uncertainty methods. Bayesian neural networks: these models can provide uncertainty estimates for predictions, allowing you to assess the confidence of the model's predictions. Monte Carlo dropout: this technique uses dropout during inference to generate multiple predictions, allowing for an estimation of prediction uncertainty. Challenges and fixes. Challenge 1: overfitting. If the model is too complex, it might overfit to the training data, leading to poor generalization performance. Sample use case that resulted in challenge 1, a complex model with many layers and parameters trained on a small dataset with high noise levels. Fixes to challenge 1. Regularization techniques. Techniques like L1 and L2 regularization can penalize model complexity. Preventing overfitting. Early stopping. Stop the training process when the model's performance on a validation set starts to decrease. Preventing overfitting. Data augmentation. Increasing the size of the training dataset by generating new data points can help improve generalization performance. Challenge 2. Poor feature representation. If the features are not informative enough, the model might struggle to learn a good decision boundary. Sample use case that resulted in challenge 2. The dataset has no additional features apart from the x and y coordinates. Fixes to challenge 2. Feature engineering. Create new features from existing ones that are more informative for the classification task. Dimensionality reduction. Techniques like PCA can reduce the dimensionality of the data while preserving important information. Kernel methods. Using kernel methods like RBF kernels can implicitly map the data into a higher dimensional space, potentially allowing for a more expressive decision boundary. sklearn. Datasets. Make classification. Description. The make classification function is a utility for generating synthetic classification datasets in scikit-learn. It allows you to create datasets with different characteristics for exploring in testing. Classification algorithms. Inputs. N samples. The number of samples to generate. N features. The number of features variables in the dataset. N informative. The number of features that are actually informative contribute to the classification. N redundant. The number of redundant features linearly dependent on the informative features. N classes. The number of classes categories to create. NC clusters per class. The number of clusters per class default to, meaning each class will have 2 clusters. Random state controls the randomness of the data generation. Setting it to an integer ensures that you'll get the same data every time. Outputs. X. The generated feature matrix. N samples. X. N features. Y. The generated target vector. N samples. Steps. Define the number of samples. Features. Informative features. Redundant features. Classes. And clusters per class. Use make classification with the specified parameters to generate the data. This function will generate random samples with specific characteristics and assign them to different classes. Return the feature matrix X and the target vector Y. Metrics. Accuracy. A common metric for classification problems. It measures the percentage of correctly classified instances. Precision. The proportion of true positives among all predicted positives. Recall. The proportion of true positives among all actual positives. F1 score. A harmonic mean of precision and recall. Visualization plots. Scatter plot. This can be used to visualize the separation of classes in the feature space. Pair plot shows the relationships between all pairs of features, highlighting any potential patterns or separation between classes. Decision boundary plot visualizes the decision boundaries of a trained classifier on the generated data. Fine-tune parameters. N informative controls the number of informative features, which influences the complexity of the task. N redundant allows you to introduce redundant features, adding noise and complexity to the dataset. NC clusters per class modifies the cluster structure within each class, affecting the decision boundary shapes. Uncertainty methods. Confidence intervals estimate the uncertainty of the model's predictions based on the generated data. Ensemble methods use multiple models to provide an ensemble prediction, with the uncertainty reflected in the variance between models. Challenges and fixes. Challenge 1: overfitting if the dataset is too small or has too many features. A model might overfit the training data and perform poorly on unseen data. Sample use case that resulted in challenge 1: using make classification with a small n samples and a large n features might lead to overfitting. Fixes to challenge 1: increase the number of samples n samples to provide more data for the model to learn from. Reduce the number of features n features to simplify the learning task. Use regularization techniques, e.g. L1 or L2 to prevent overfitting. Use cross-validation to evaluate the model's performance on unseen data. Challenge 2: class imbalance if the number of samples in different classes is significantly different. The model might be biased towards the majority class. Sample use case that resulted in challenge 2: if you use make classification to generate a dataset with a very uneven distribution of samples across classes, it can lead to class imbalance. Fixes to challenge 2: use oversampling techniques, e.g. SMOT to increase the number of samples in minority classes. Use undersampling techniques to reduce the number of samples in majority classes. Use cost-sensitive learning techniques that assign different costs to errors made on different classes. Use appropriate evaluation metrics that are not sensitive to class imbalance, such as the F1 score. sklearn, datasets, make Friedman 1. Description. This function generates a synthetic dataset with nonlinear relationships between features and target. It is designed for regression problems and is useful for testing and comparing different regression models. Inputs. N samples, the number of samples to generate. N features, the number of features to generate. Random state, an integer value to control the randomness of the dataset generation. X, a numpy array of shape n samples. N features representing the features. Y, a numpy array of shape n samples, representing the target values. It generates random samples for each feature X using a uniform distribution. It calculates the target value Y based on the following formula. Y 10 simpy X, 0x, 120x, 2 to 0.5 to 10x, 3 5x, 4 noise, where noise is random noise added to the output. Mean squared error MSE. R squared. Scatter plots of each feature against the target variable. Pairwise scatter plots of the features. N samples, higher values can create more diverse datasets, but may lead to longer training times. N features, more features can introduce more complex relationships, but may require more sophisticated models. Bootstrap aggregating bagging. Random forest. Challenge 1: overfitting with too many features. This can occur when the number of features is significantly larger than the number of samples, leading to models that perform well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: training a linear regression model on a dataset with 100 features and only 50 samples. Fixes to challenge 1: feature selection, remove irrelevant or redundant features to reduce the dimensionality of a dataset. Regularization techniques like L1 and L2 regularization can penalize models with large coefficients, reducing overfitting. Challenge 2: difficult to interpret the relationships between features and target due to the nonlinear nature of the generated data. Understanding the impact of each feature on the target can be challenging. Sample use case that resulted in challenge 2: trying to understand the relationship between a specific feature and the target variable using a linear regression model. Fixes to challenge 2. Feature engineering, transform or combine features to create new features that may have a clearer linear relationship with the target. Use nonlinear models. Consider using models like decision trees, support vector machines, or neural networks, which can better capture nonlinear relationships. sklearn, datasets, Make-Friedman 2. Description. This function generates a synthetic dataset with a nonlinear relationship between the input features and the target variable. The dataset is designed to be challenging for linear models and is commonly used to test the performance of nonlinear machine learning algorithms. It mimics the Friedman 1 problem, but with an additional 5 input features. Inputs. N samples, the number of samples to generate. This determines the size of the dataset. N features, the number of input features to generate. This controls the dimensionality of the dataset. Random state, the seed for the random number generator. This ensures reproducibility of the generated dataset. Outputs. X, the input features, represented as a NumPy array of shape n samples. N features. Y, the target variable, represented as a NumPy array of shape n samples. Steps. The function first generates random samples from a uniform distribution. Then, it calculates the target variable y based on a nonlinear function involving the input features x. This function is designed to introduce nonlinearity and complexity into the data. Metrics. R-squared, a measure of how well the model explains the variance in the target variable. It is commonly used to evaluate the performance of regression models. Mean squared error, MSE, a measure of the average squared difference between the predicted and actual values. It is a common metric for evaluating regression models. Visualization plots. Scatter plots to visualize the relationship between the input features and the target variable. Scatter plots can be used. This can help identify any nonlinear patterns in the data. Pair plots. These plots show the relationship between all pairs of features and the target variable. They can reveal complex dependencies and potential interactions. Fine-tune parameters. N samples, adjust this parameter to create a dataset with the desired number of samples. N features. This parameter determines the number of input features, allowing you to control the complexity and dimensionality of the dataset. Random state setting. This parameter ensures that the generated dataset is reproducible. Uncertainty methods. Bootstrap aggregating bagging. This method can be used to estimate the uncertainty in the models. Predictions. It involves creating multiple models using random subsets of the data and averaging their predictions. Bayesian inference. This method can be used to estimate the posterior distribution of the model. Parameters. Providing information about the uncertainty in the model's predictions. Challenges and fixes. Challenge 1, overfitting. This happens when a model learns the training data too well, resulting in poor performance on unseen data. Sample use case that resulted in challenge 1, using a complex model like a deep neural network with a small dataset might lead to overfitting. Fixes to challenge 1. Use regularization techniques like L1 or L2 regularization to penalize complex models. Employ cross-validation to assess the model's performance on unseen data and adjust its complexity accordingly. Challenge 2, feature engineering. Selecting the right features and transforming them appropriately can significantly improve model performance. Sample use case that resulted in challenge 2, using raw features with high dimensionality and irrelevant information may hinder model performance. Fixes to challenge 2. Apply dimensionality reduction techniques like PCA or feature selection methods to identify and use the most relevant features. Engineer new features based on domain knowledge or insights gained from data exploration. sklearn, datasets, Make-Friedman 3. Description. This function generates a synthetic dataset designed to test the effectiveness of regression algorithms. It simulates a nonlinear relationship between the input features and the target variable, making it a good benchmark for evaluating model performance in handling complex relationships. N samples the number of samples data points to generate in the dataset. N features the number of input features independent variables in the dataset. Random state an integer value used to initialize the random number generator. This ensures reproducibility, meaning that you'll get the same dataset every time you run the function with the same random state. X a NumPy array containing the generated input features. Each row represents a data point, and each column represents a feature. Y a NumPy array containing the generated target variable dependent variable. Steps. The function starts by generating n samples, random samples for each of the n features. It then calculates the target variable y based on the following formula. Y10 simpy x, 0x, 120x, 2 to 0.5 to 10x, 3 5x, 4. This formula incorporates nonlinear interactions between the first two features, a quadratic term for the third feature, and linear terms for the remaining features. Metrics. R-squared R2 a common metric used to assess the goodness of fit of a regression model. It measures the proportion of the variance in the target variable that is explained by the model. A higher R2 score indicates a better fit. Mean squared error MSE another widely used metric for regression models. It calculates the average squared difference between the predicted values and the actual values. A lower MSE implies a more accurate model. Visualization plots. Scatter plots visualize the relationship between individual features and the target variable to understand the nonlinear patterns in the data. Pair plots create a matrix of scatter plots to show the relationships between all pairs of features and the target variable. N samples adjust the number of samples to control the size of the dataset. A larger dataset may lead to more robust model training. N features alter the number of input features to test the model's ability to handle varying feature complexities. Confidence intervals use statistical methods to estimate the uncertainty around the predicted values. This can be helpful for assessing the reliability of model predictions. Bayesian methods employ probabilistic models to capture the uncertainty in the model parameters and generate predictions with associated uncertainties. Challenge 1 overfitting. When a model learns the training data too well, it may not generalize well to unseen data. Sample use case. If the model is trained on a small dataset, it might memorize the specific patterns in the training data and fail to capture the underlying relationships. Fixes. Regularization techniques e.g. L1 or L2 regularization can be applied to penalize overly complex models and prevent overfitting. Cross-validation can be used to evaluate the model's performance on unseen data and identify potential overfitting. Challenge 2 feature scaling. Different ranges of values in features can affect the performance of some algorithms. Sample use case. If one feature has a much larger scale than others, it may dominate the optimization process, leading to suboptimal results. Fixes. Scaling techniques e.g. standardization or normalization can be applied to bring features to a common scale. This can improve the performance of algorithms that are sensitive to feature scales. Challenge 3 Model selection. Choosing the right regression model for the dataset is crucial. Sample use case. A linear regression model might not be suitable for a dataset with strong nonlinear relationships. Fixes. Experiment with different models, e.g., decision trees. Support vector machines, neural networks to find the best fit for the data. Feature engineering can be used to create new features that better capture the underlying relationships in the data. sklearn datasets make Gaussian quantiles. Description. This function generates a dataset with two classes, where the data is drawn from two multivariate Gaussian distributions with different means. The classes are separated by quantiles of a one-dimensional projection of the data. Inputs. Mean. The mean of the first Gaussian distribution. This is a list of values representing the mean of each dimension of the distribution. For example, if the data has two dimensions, mean could be 1, 2. Cov. The covariance matrix of the first Gaussian distribution. This is a 2D array representing the covariance between each dimension of the distribution. The size of the array should match the number of dimensions in the data. N samples. The total number of samples to generate for both classes. N features. The number of dimensions in the data. N classes. The number of classes to generate. The default is 2. Random state. A seed for the random number generator. This ensures that the same dataset is generated each time the function is called with the same seed. Outputs. X. The generated data. This is a 2D array where each row represents a data point and each column represents a feature. Y. The class labels for the data. This is a 1D array where each element is the class label for the corresponding row in X. Steps. Generate two multivariate Gaussian distributions with the specified means and covariances. Generate data points from each distribution, based on N samples and N features. Project the data points onto a one-dimensional subspace. Separate the data points into two classes based on quantiles of the projected values. Metrics. Accuracy. The percentage of data points that are correctly classified. Precision. The percentage of data points that are classified as positive that are actually positive. Recall. The percentage of data points that are actually positive that are classified as positive. Visualization plots. Scatter plot of the data points, colored by class label. Histogram of the projected values, showing the quantiles used to separate the classes. Fine-tune parameters. Mean. Changing the mean of the Gaussian distributions will shift the centers of the clusters. Cov. Adjusting the covariance matrix will change the shape and spread of the clusters. N features. Increasing the number of features will create a higher dimensional dataset. Uncertainty methods. Confidence intervals for the mean of each cluster. Challenges and fixes. Challenge 1. The data may be linearly inseparable, making it difficult to classify using linear models. Sample use case that resulted in challenge 1 when the means of the two Gaussian distributions are very close together, or the covariance matrices are very different. The data may be linearly inseparable. Fixes to challenge 1. Use a nonlinear classifier, such as a support vector machine with a nonlinear kernel. Challenge 2. The data may be highly imbalanced, with one class having many more samples than the other. Sample use case that resulted in challenge 2. If N samples is not evenly divided between the two classes, the data will be imbalanced. Fixes to challenge 2. Use a sampling technique, such as oversampling the minority class or undersampling the majority class. sklearn datasets Make-Hasty 102. Description. This function generates a synthetic dataset based on the Hasty, Tibshirani and Friedman 2009 textbook. It is a classic example used for demonstrating the effectiveness of different machine learning algorithms, particularly for showcasing the impact of feature interactions and nonlinear relationships on model performance. Inputs. N samples the number of data points to generate in the dataset. This parameter controls the size of the dataset. Random state and integer seed value used to initialize the random number generator. Setting a fixed value ensures reproducibility of the generated dataset. X the feature matrix of the generated dataset. Each row represents a data point, and each column represents a feature. The dataset has 10 features columns. Y the target variable vector. This is a vector containing the labels or responses corresponding to each data point in the feature matrix. The dataset has two classes 0 and 1. Steps. Create a dataset with n samples data points and 10 features. Define the relationship between the features and the target variable based on the Hasty, Tibshirani and Friedman 2009 textbook example. Generate random data points for each feature based on a normal distribution with mean 0 and standard deviation 1. Create the target variable y based on the defined relationship with the features. The target variable is binary 0 or 1, representing the two classes in the dataset. Metrics. Accuracy measures the proportion of correctly classified data points. This metric is commonly used for binary classification problems. AUC area under the ROC curve evaluates the ability of a model to distinguish between the two classes. It represents the area under the receiver operating characteristic ROC curve. Visualization plots. Scatter plots can be used to visualize the distribution of data points in the feature space and identify potential patterns or relationships between features. Pair plots show the relationships between all pairs of features, allowing for the identification of potential correlations and interactions. Decision boundary plots depict the decision boundary learned by a model. This can be useful for understanding how a model classifies data points based on the feature values. N samples adjusting the number of data points can impact the complexity and size of the dataset. Random state. Different random states can result in different datasets, which can influence model training and evaluation. Confidence intervals quantify the uncertainty in model predictions. Bayesian methods provide a probabilistic framework for incorporating uncertainty into model estimation. Challenge 1. Overfitting. When a model learns the training data too well, it may not generalize well to unseen data. Sample use case that resulted in challenge 1. A complex model with a high number of features or parameters trained on a small dataset. Fixes to challenge 1. Regularization techniques. Techniques like L1 and L2 regularization penalize complex models and prevent overfitting. Cross-validation. Splitting the data into multiple folds for training and testing helps evaluate model performance on unseen data and prevent overfitting. Challenge 2. Feature interactions. The presence of interactions between features can make it difficult to interpret and model the data. Sample use case that resulted in challenge 2. The Hasty, Tibshirani and Friedman 2009 dataset has complex relationships between features, which can be challenging to capture with linear models. Fixes to challenge 2. Feature engineering. Creating new features that capture the interactions between existing features. Nonlinear models. Using models such as decision trees, support vector machines with nonlinear kernels. Or neural networks can handle nonlinear relationships between features. sklearn, datasets, Maclaurin matrix. Description. This function generates a random low-rank matrix with specified dimensions and a desired rank. It's useful for creating synthetic datasets where the underlying data structure has a low rank. Representation, which can be used to simulate real-world scenarios like collaborative filtering or image compression. Inputs. N samples the number of rows in the generated matrix. N features the number of columns in the generated matrix. Effective rank, the desired rank of the generated matrix. It represents the number of non-zero singular values in the singular value decomposition SVD of A matrix. Outputs. X, the generated low-rank matrix of shape N samples. N features the true low-rank factors used to generate the matrix, in the form of two matrices N samples. Effective rank and effective rank. N features. Steps. Generate two random matrices, one of shape N samples. Effective rank and the other of shape effective rank. N features. Multiply these matrices to obtain a low-rank matrix of shape N samples. N features. Metrics. Rank, the actual rank of the generated matrix, which should be close to the specified effective rank. Singular value spectrum, the distribution of singular values, which should exhibit a clear drop-off after the effective rank. Visualization plots. Singular value spectrum, a plot showing the singular values in descending order, highlighting the drop-off after the effective rank. Heat map, a heat map of the generated matrix, showing the structure and potential patterns. Fine-tune parameters. Effective rank, adjust the desired rank to control the complexity of the generated matrix. Higher values result in more complex and potentially noisy data. Random state seed for the random number generator, ensuring reproducibility of the results. Uncertainty methods. Bootstrap, generate multiple low-rank matrices with the same parameters and observe the variation in the generated data to estimate uncertainty. Monte Carlo simulation, simulate different values for the input parameters, such as effective rank, and measure the impact on the resulting matrix. Challenges and fixes. Challenge 1. Generating a matrix with an exact rank. The generated matrix may have a slightly higher rank than the specified effective rank due to numerical precision issues. Sample use case that resulted in challenge 1 when trying to generate a matrix with an effective rank of 10. The resulting matrix might have a rank of 11 due to numerical rounding. Fixes to challenge 1. Use a tolerance value when calculating the rank, allowing for small variations from the specified effective rank. Challenge 2. The generated data may not be representative of real-world data. The random matrices used in the generation process may not accurately reflect the underlying structure of real-world data sets. Sample use case that resulted in challenge 2. The generated data might not exhibit the same patterns or trends as observed in actual low-rank datasets. Fixes to challenge 2. Consider incorporating additional constraints or assumptions about the data during generation. Use domain knowledge to guide the selection of parameters, ensuring the generated data reflects real-world characteristics. sklearn, datasets, make moons. Description. This function generates a synthetic 2-moon dataset, which is a classic example of a non-linearly separable dataset. It's used for testing and evaluating machine learning models, particularly those that can learn nonlinear decision boundaries. Inputs. N samples, the number of data points to generate. Noise, the amount of noise to add to the data. This controls how much the 2 moons are smeared together. Random state a seed for the random number generator. Setting this allows you to reproduce the same dataset. Outputs. X a 2D array of shape n samples. 2. Representing the features of the data points. Y a 1D array of shape n samples. Representing the class labels for the data points. Steps. The function creates two half-moon-shaped clusters of data points in a 2D space. It adds Gaussian noise to the data points, making them overlap slightly and making the separation nonlinear. It assigns class labels to the data points based on which cluster they belong to. Metrics. Accuracy, a measure of how well a classification model predicts the correct class labels. Precision, a measure of how many of the positive predictions made by a classifier are actually correct. Recall, a measure of how many of the actual positive cases are correctly identified by a classifier. F1 score, a balanced measure of precision and recall. Visualization plots. Scatter plot. A scatter plot can be used to visualize the data points and their class labels, showing the two moon shapes and the degree of overlap. Fine-tune parameters. N samples adjust the number of data points to create datasets of varying size for testing. Noise. Vary the noise level to control the degree of difficulty in separating the two moons. Uncertainty methods. Bayesian methods can be used to estimate the uncertainty of predictions on the generated data. Challenges and fixes. Challenge 1. Overlapping data points. The noise parameter can cause the two moons to overlap significantly, making it difficult for some models to separate the classes effectively. Sample use case that resulted in challenge 1. A model trained on a dataset with high noise might struggle to correctly classify data points in the overlapping region. Fixes to challenge 1. Reduce the noise parameter. Lowering the noise level will reduce the overlap and make a separation easier. Use more sophisticated models that are specifically designed to handle nonlinear decision boundaries, such as support vector machines with a nonlinear kernel, might be more effective. Challenge 2. Limited feature space. The dataset is limited to 2 features, which might not be sufficient for testing models that can handle higher dimensional data. Sample use case that resulted in challenge 2. Using the MakeMoons dataset to evaluate a model designed for image recognition, which typically involves hundreds or thousands of features, might not be representative. Fixes to challenge 2. Explore other datasets for testing high-dimensional models. Use other datasets such as MNIST or CIFAR10, which have more features. Modify the dataset. Extend the MakeMoons dataset to include more features by creating additional synthetic variables. sklearn datasets make multi-label classification. Description. This function generates a multi-label classification dataset with configurable properties. It allows you to create synthetic datasets for experimenting with and evaluating multi-label classification algorithms. Inputs. N samples. Number of samples to generate. N features. Number of features variables in the dataset. N classes. Number of classes labels for each sample. N labels. Average number of labels per sample. Length of the generated labels. It controls the number of unique values within each label, impacting the complexity of the multi-label classification problem. Allow unlabeled. Whether to allow samples without labels. Random state controls the random number generator for reproducible results. Return indicator. Whether to return the label matrix as a binary indicator matrix or as a list of lists. Outputs. X. The generated feature matrix with shape n samples. N features. Y. The generated label matrix. It can be a binary indicator matrix with shape n samples. n classes if return indicator is true. Or a list of lists with shape n samples, if return indicator is false. Steps. The function generates a feature matrix X with random values. The function generates label matrices for each class with random values. For each sample, a specific number of labels is chosen randomly. The chosen labels are assigned to the respective sample in the label matrix. The function returns the feature matrix X and the label matrix Y. Metrics. Accuracy, a measure of the proportion of correctly classified samples. Precision, the ratio of correctly predicted positive samples to all predicted positive samples. Recall, the ratio of correctly predicted positive samples to all actual positive samples. F1 score, the harmonic mean of precision and recall, providing a balanced evaluation of the model's performance. Hamming loss, the average number of incorrectly predicted labels per sample. Visualization plots. Scatter plots to visualize the distribution of features. Heat maps to visualize the correlation between features and labels. Confusion matrices to visualize the model's predictions and actual labels. Fine-tune parameters. N samples increase the number of samples to improve the model's generalization ability. N features increase the number of features to make the problem more challenging. N classes increase the number of classes to increase the complexity of the problem. N labels increase the number of labels per sample to increase the number of possible label combinations. Length increase the length of the labels to increase the number of unique values within each label, making the problem more complex. Uncertainty methods. Confidence scores assign confidence scores to each prediction, indicating the model's certainty about the assigned labels. Bayesian methods employ Bayesian inference to model the uncertainty in the model parameters and predictions. Challenges and fixes. Challenge 1. Imbalanced labels. When the number of samples with certain labels is significantly higher than others, the model might be biased towards the majority labels. Sample use case. A multi-label dataset where a few labels have many samples while others have very few. Fixes. Endosampling removes samples from the majority labels. Oversampling duplicate samples from the minority labels. Weighing assign higher weights to the minority labels during training. Challenge 2. High cardinality labels. If the number of unique values within a label is very large, it might be difficult for the model to learn the relationships between labels and features. Sample use case. A dataset where a label has a large number of possible values. Fixes. Label encoding convert the labels into a numerical representation. Feature engineering create new features based on the label values. Hierarchical classification group labels into hierarchies to reduce the number of unique values. Challenge 3. Large number of classes with a large number of classes. The model might struggle to learn the relationships between features and labels effectively. Sample use case. A dataset with a very high number of classes. Fixes. Feature selection. Select the most informative features. Ensemble methods combine multiple models to improve performance. Regularization. Use techniques like L1 or L2 regularization to prevent overfitting. sklearn. Datasets. Make regression. Description. This function generates a synthetic regression dataset with a specified number of samples, features, and target values. It provides a controlled environment for testing and developing regression models. Inputs. N samples, the number of samples to generate. N features, the number of features for each sample. N informative, the number of features that are actually used to generate the target values. N targets, the number of target values to generate. Bias, the bias term added to the generated target values. Effective rank, the rank of the coefficient matrix, which influences the degree of collinearity among features. Tail strength, the strength of the tail distribution for feature values. Noise, the amount of random noise added to the target values. Shuffle, whether to shuffle the generated data. Random state, the random seed for reproducibility. Outputs. X, the generated feature matrix, where each row represents a sample and each column represents a feature. Y, the generated target values. Steps. Generate a random coefficient matrix with the specified effective rank and n features. Generate a random feature matrix with the specified n samples and n features. Calculate the target values by multiplying the feature matrix with the coefficient matrix, adding the bias term, and applying noise. Metrics. R-squared measures the proportion of variance in the target variable that is explained by P. Features. Mean squared error. MSE measures the average squared difference between the predicted and actual target values. Root mean squared error. RMSE, the square root of MSE, providing a more interpretable measure of error. Visualization plots. Scatter plots visualize the relationship between each feature and the target variable. Residual plots plot the difference between predicted and actual target values to identify patterns or outliers. Fine-tune parameters. N samples adjust the number of samples to match the size of the real-world dataset. N features choose the number of features relevant to the problem being modeled. N informative set the number of features that contribute meaningfully to the target variable. Bias adjust the bias term to account for any inherent offset in the data. Noise adjust the noise level to mimic the real-world data's variability. Uncertainty methods. Confidence intervals quantify the uncertainty in the predicted target values. Prediction intervals provide a range within which future target values are likely to fall. Challenges and fixes. Challenge 1. The generated data may not reflect the complexity or specific characteristics of real-world datasets. Sample use case. When modeling financial data, the generated data may not capture the time series dependencies present in real-world financial data. Fixes. Use real-world datasets or augment the generated data with domain-specific features or temporal relationships. Challenge 2. The generated data may have high collinearity between features, leading to unstable model estimates. Sample use case. When modeling health data, multiple features like age, weight, and blood pressure might be highly correlated. Fixes. Consider using regularization techniques like lasso or ridge regression to mitigate the effects of collinearity. Challenge 3. The default values of the parameters may not be suitable for all use cases. Sample use case. The default noise level may be too high or too low for a specific application, leading to unrealistic data generation. Fixes. Experiment with different parameter values to find the optimal settings for the desired data characteristics. sklearn, datasets, makes curve. Description. This function generates a synthetic three-dimensional dataset resembling an S-shaped curve embedded in a 3D space. This dataset is often used for demonstrating dimensionality reduction techniques and manifold learning algorithms due to its nonlinear, curved structure. Inputs. N samples, the number of samples to generate. Noise, the standard deviation of the Gaussian noise to add to the generated data. Outputs. X, the generated dataset of shape N samples. 3. Representing the 3D coordinates of each sample point. T, the underlying parameter values of the S-curve. This is a one-dimensional array of shape N samples. representing the position of each sample point along the curve. Steps. The function first generates a set of evenly spaced parameter values t within a specified range. Then, it applies a mathematical function to these parameter values to generate the corresponding 3D coordinates x that form the S-curve. Finally, Gaussian noise is added to the generated coordinates to introduce some randomness and mimic real-world data. Metrics. None specifically defined, as this is a dataset generation function, not a model. Visualization plots. 3D scatter plot. This is the most common visualization to showcase the S-curve structure. Plotting the generated points in 3D space. 2D projections. Projecting the 3D points onto different 2D planes can reveal the underlying structure and how the S-curve is embedded in the higher dimensional space. Fine-tune parameters. N samples controls the size of the dataset. Increasing it can provide more data points for analysis. Noise adjusts the level of noise added to the data. Higher noise values introduce more randomness and make the S-curve less smooth. Uncertainty methods. None specifically applicable, as this is a dataset generation function, not a model. Challenges and fixes. Challenge 1. Overfitting to the generated S-curve. Sample use case that resulted in challenge 1. Applying a model that learns the exact shape of a S-curve, leading to poor generalization performance on unseen data. Fixes to challenge 1. Use regularization techniques to prevent overfitting. Increase the noise level during dataset generation to make the curve less perfect. Employ model selection methods like cross-validation to choose the best model complexity. Challenge 2. Difficulty in visualizing the 3D S-curve structure due to its complexity. Sample use case that resulted in challenge 2. Failing to grasp the full picture of the S-curve when attempting to visualize it in 2D projections. Fixes to challenge 2. Utilize interactive 3D visualization tools for better exploration of the data. Experiment with different projection techniques and angles to get a clearer view. Combine visualizations with other analytical methods to gain deeper insights. sklearn datasets make sparse-coded signal. Description. This function generates a signal that is a sparse combination of dictionary elements. It simulates the process of representing a signal using a few basis vectors from a larger dictionary. This process is often used in compressed sensing and sparse coding applications. Inputs. N samples the number of signals to generate. N components the number of dictionary elements. N features the number of features in each signal. N non-zero coefs the number of non-zero coefficients in the sparse code for each signal. Random state the seed for the random number generator. Outputs. X the generated signals N samples. N features array. Dictionary the dictionary matrix used to generate the signals N features. N components array. Core the sparse codes used to generate the signals N samples. N components array. Steps. Generate a random dictionary matrix with N features rows and N components columns. Generate random sparse codes with N samples rows and N components columns, where each row has N non-zero coefs non-zero elements. Multiply the dictionary matrix by the sparse codes to obtain the signals. Metrics. Sparsity measures the fraction of non-zero elements in the sparse codes. Reconstruction error measures the difference between the original signals and the signals reconstructed using the dictionary and sparse codes. Visualization plots. Scatter plot of the dictionary elements. Heat map of the sparse codes. Reconstruction error plot. Fine-tune parameters. N components the number of dictionary elements. Increasing this value may lead to a more accurate representation of the signals. but it may also increase computational complexity. N non-zero coefs, the number of non-zero coefficients in the sparse code. Increasing this value may lead to a more complex representation of the signals. But it may also increase the difficulty of finding a sparse solution. Uncertainty methods. Monte Carlo simulation generate multiple sets of signals and sparse codes using different random seeds and calculate the mean and standard deviation of the reconstruction error. Challenges and fixes. Challenge 1: difficulty in finding sparse solutions when the dictionary is highly correlated or the signals are very noisy. Sample use case that resulted in challenge 1: trying to find a sparse representation of a signal with high noise using a dictionary with highly correlated elements. Fixes to challenge 1: use a more robust dictionary learning algorithm that is less sensitive to noise and correlation. Use a regularization technique to penalize the number of non-zero coefficients in the sparse codes. Challenge 2: difficulty in interpreting the meaning of the sparse codes when the dictionary elements are not easily interpretable. Sample use case that resulted in challenge 2: trying to interpret the sparse codes for a signal generated using a dictionary of random numbers. Fixes to challenge 2: use a dictionary with elements that have a clear physical meaning. Visualize the sparse codes using a heat map or other visualization tools to gain insight into their structure. sklearn datasets make sparse SPD matrix. Description: this function generates a sparse symmetric positive definite SPD matrix. SPD matrices are commonly used in various machine learning applications, particularly in Gaussian process regression and kernel methods. Inputs: n samples, the number of samples rows to generate. Random state determines the random number generation for reproducibility. Providing an integer value ensures that the generated matrix will be the same across multiple runs. Alpha controls the sparsity of the resulting matrix. Lower values of alpha lead to denser matrices. Outputs: sparse matrix, a sparse SPD matrix represented using the SciPy sparse matrix format. Random state, the random number generator object used for the generation. Steps: generate a dense random matrix using NP random RANDN. Compute its covariance matrix using NP dot matrix T matrix. Convert the covariance matrix into a sparse format. Add a small constant value alpha to the diagonal of the sparse matrix. This ensures that the matrix is positive definite. Metrics: sparsity, the ratio of non-zero elements in the matrix. Condition number, a measure of the matrix's sensitivity to small changes in its entries. Visualization plots: heatmap, a graphical representation of the sparse matrix. Fine-tune parameters: n samples. Adjusting this parameter allows you to generate matrices with varying numbers of samples. Alpha: by changing alpha, you can control the density of the generated sparse matrix. Smaller alpha values result in denser matrices. Uncertainty methods: confidence intervals in applications where the generated matrix represents uncertainties. Confidence intervals can be calculated for the estimated values. Challenges and fixes: challenge 1: the generated sparse matrix might not be perfectly positive definite in extreme cases of sparsity. Sample use case that resulted in challenge 1: when using a very small value for alpha, the matrix might have near zero eigenvalues, making it nearly singular. Fixes to challenge 1: increase the value of alpha slightly to ensure positive definiteness. Challenge 2: the random state might not be consistently preserved across different versions of Scikit-learn. Sample use case that resulted in challenge 2 if you run the same code with different versions of Scikit-learn. You might get different results. Fixes to challenge 2. Use a fixed seed for the random number generator for consistent results. Consider using a version-independent random number generator if possible. sklearn. Datasets. Make sparse uncorrelated. Description. This function generates a random sparse dataset with uncorrelated features. It is useful for creating synthetic data to test the performance of machine learning models that are designed to handle sparse data. Inputs. N samples the number of samples to generate. N features the number of features to generate. Random state the seed for the random number generator. This ensures that the generated data will be consistent across multiple calls to the function. Density. The desired density of the generated dataset. This refers to the proportion of non-zero values in the dataset. The default value is 0.1, which means that 10 of the values in the dataset will be non-zero. D-type. The data type of the generated dataset. This can be any data type that is supported by NumPy. The default value is float 64. Outputs. X. A NumPy array of shape n samples. N features containing the generated data. Each row of the array corresponds to a sample, and each column corresponds to a feature. Y. A NumPy array of shape n samples, containing the target values for the generated data. The target values are generated randomly from a uniform distribution. Steps. A sparse matrix with random non-zero entries is generated. The density of the matrix is controlled by the density parameter. The target values are generated randomly from a uniform distribution. Metrics. Sparsity. The proportion of non-zero values in the generated dataset. Correlation. The correlation between the features in the generated dataset. This should be close to 0 for uncorrelated features. Visualization plots. Scatter plot. This can be used to visualize the distribution of the data in 2 dimensions. Heat map. This can be used to visualize the correlation between the features. Fine-tune parameters. Density. This parameter controls the sparsity of the generated dataset. A higher value of density will result in a denser dataset. N samples. This parameter controls the number of samples in the generated dataset. N features. This parameter controls the number of features in the generated dataset. Uncertainty methods. None. Challenges and fixes. Challenge 1. The generated dataset may have a high number of zero values, which can make it difficult to train some machine learning models. Sample use case that resulted in challenge 1 using the dataset to train a linear regression model. Fixes to challenge 1. Use a machine learning model that is designed to handle sparse data, such as a sparse linear regression model. Challenge 2. The generated data may not be realistic. Sample use case that resulted in challenge 2 using the dataset to train a model to predict the price of a house. Fixes to challenge 2. Use a different dataset generation function that generates more realistic data. sklearn. Datasets. Make SPD matrix. Description. This function generates a random symmetric positive definite SPD matrix. SPD matrices are important in various areas of mathematics and statistics, including linear algebra, optimization, and machine learning. They are used to represent covariance matrices, kernel matrices, and other positive definite structures. Inputs. N samples the number of rows and columns of the generated SPD matrix. Random state. An integer, a random state instance, or none default. If int Random state is the seed used by the random number generator if random state instance. Random state is the random number generator if none. The random number generator is the random state instance used by NP. Random. Outputs. WAN samples. N samples NumPy array representing the generated SPD matrix. Steps. Generate a random matrix A of shape N samples. N samples using the specified random state. Compute the square of A2. Return A2 as the SPD matrix W. Matrix. Determinant. The determinant of the generated matrix is a measure of its volume. Trace. The trace of the matrix is the sum of its diagonal elements and is related to the average. Eigenvalue. Visualization plots. Heat map. Visualize the SPD matrix using a heat map to understand the distribution of its elements and identify potential patterns. Eigenvalue spectrum. Plot the eigenvalues of the SPD matrix to analyze its spectral properties and understand its scaling behavior. Fine-tune parameters. N samples adjust the number of rows and columns of the SPD matrix to control the complexity of a generated matrix and its potential applications. Random state. Control the randomness of the generated SPD matrix by specifying a seed or providing a random state instance. Uncertainty methods. None. The make SPD matrix function does not inherently involve uncertainty. It directly generates a deterministic SPD matrix. Challenges and fixes. Challenge 1. The generated SPD matrix may have a very small determinant, leading to numerical instability in subsequent calculations. Sample use case that resulted in challenge 1 when used in optimization algorithms. A matrix with a very small determinant can cause the optimizer to get stuck in local optima or fail to converge. Fixes to challenge 1. Increase the number of samples. Generating a larger SPD matrix can lead to a higher determinant and improve numerical stability. Use a different method. Explore alternative methods for generating SPD matrices that ensure a minimum determinant. Challenge 2. The generated SPD matrix may have a large dynamic range, making it difficult to interpret and visualize its elements. Sample use case that resulted in challenge 2 when visualizing the matrix with a heat map. A large dynamic range can make it difficult to discern the relative magnitudes of different elements. Fixes to challenge 2. Scale the matrix. Normalize the matrix elements to a smaller range using techniques like min-max scaling or Z-score normalization. Use a logarithmic color scale. Plot the heat map using a logarithmic color scale to better visualize the relative magnitudes of the elements, especially for matrices with a large dynamic range. sklearn datasets make Swiss roll. Description. This function generates a synthetic dataset resembling a 2D Swiss roll embedded in a 3D space. It's often used for demonstrating dimensionality reduction techniques and manifold learning algorithms. Inputs. N samples. The number of data points to generate. Noise. The level of Gaussian noise to add to the data points. Random state. The seed for the random number generator. Outputs. X. A NumPy array of shape N samples. 3 representing the generated data points in 3D space. T. A NumPy array of shape N samples, representing the values of the T parameter, which determines the position of a point on the Swiss roll. Steps. Generates a sequence of values for the T parameter, ranging from 0 to 15. Calculates the X, Y, and Z coordinates of each data point based on the corresponding T value. Introduces Gaussian noise to the coordinates. Metrics. No specific metrics are associated with the data generation process itself. However, The quality of the generated dataset can be evaluated indirectly by observing how well dimensionality reduction algorithms recover the underlying manifold, the Swiss roll, from the noisy data. Visualization plots. 3D scatter plot of the generated data points, illustrating the Swiss roll structure. 2D scatter plot of the data after dimensionality reduction, showing the recovered manifold. Fine-tune parameters. N samples controls the number of data points generated, affecting the density and size of the Swiss roll. Noise influences the level of noise added to the data, impacting the difficulty of recovering the underlying manifold. Uncertainty methods. No specific uncertainty methods are used in the generation process. Challenges and fixes. Challenge 1. The generated data points are inherently noisy, potentially making it difficult for some algorithms to effectively recover the underlying manifold. Sample use case. When using a dimensionality reduction algorithm that assumes low noise, the noise might lead to poor performance in capturing the Swiss roll structure. Fixes. Pre-processing the data with noise reduction techniques, such as smoothing or filtering, can mitigate the impact of noise and improve the performance of algorithms. Challenge 2. The generated data is highly nonlinear, which can be challenging for some linear dimensionality reduction methods. Sample use case. Using a principal component analysis (PCA) algorithm, which is linear, on the Swiss roll dataset might not effectively capture the nonlinear structure. Fixes. Employing nonlinear dimensionality reduction methods, such as isomap or locally linear embedding (LLE), which are better suited for handling nonlinear data, can achieve more accurate results.